Mais ou menos. Eu sou minha
Eu vi o texto e o último número que eu sei que foi o
mas por acaso eu preciso assistir. Eu fiz a história. Mas outro texto, mas é muito mais conhecimento.
Era sobre velocidade.
It's there.
Aqui foi uma
It's
lista
there.
de peixes. Eu não sei do
Then we put you on the shoulders of Carlo, and then we put you there, and then you're close to the microphone. Do you want to ask questions now? So where are you from? Yeah, sure. You know all the just like in Bulgaria. Really fat in the stove, fat in the stove.
Deve ter sido a última.
Não, a comunidade muito bom, nós também temos assim, nós ainda temos 2 quadros e um projeto, nós estamos a mudar. E isso parece interessante.
Do you check the YouTube? You're okay?
No.
To check whether we're okay.
But if I check, the numbers will increase and we will attract more people.
I have more followers. No, that basic line. Huh?
Back then, I have more likes.
Uh-huh. We can do more likes in the YouTube. I didn't know we can do likes in YouTube.
Yes, you can do likes.
In the first session, I was obsessed enough.
You need to have an account in YouTube.
No, you don't have to.
Likes.
Oh, for the likes in you. Yeah.
Eu vi que as nossas salas todas por aqui fora
Não temos alguns já são outros. O CP3 só há também
No, but I'm surprised because I see the screen. We want to see you. We want to see you on the screen.
It's maybe that's smaller.
This guy? No.
At least before starting, we should check if the computer is unmuted.
Yeah.
That's in the other session.
Yeah, but that okay, it was this computer.
No, that computer, I can, because before I get up, I will.
Oh, okay. That's important.
Yeah.
So for the questions, we have to, the microphone is over here. So but you can stand on the, you can come here, you can stand on the table, and then it's all feasible.
Where is your mouse?
Oh, you need the old people mouse. No?
Yes.
Yeah, don't need to use.
Should have more old people mouses, no? Yeah, you're there. You found it, no?
Thank you. I don't see the.
And imagine these thousands of people that are watching us now. So,
Do you see the
listen
mouse?
to the mouse?
No? Ah. So where is the microphone? Oh, it's on.
It's on now.
Yeah.
Okay, we're safe.
Yeah. Okay.
You put it in.
I don't like the mouse.
He doesn't like the port.
Or I don't know if there's another port. Let me see this way.
That's right.
I don't think it's too busy. Oh, here you come.
Chunk.
Only the
Done.
Me?
Actually, give me your mouse.
Mouse. I'm in the computer science department, hardware, so I should know what's a mouse, no? That's the most important thing. You have to change the. Sorry. So we have an expert here. Okay. Helping us. Very good. So we're going to do a session with 5 presentations, the last 2 online. And Maria is already gaining points because she's from this university and she's presenting over here and not online like other people. Okay, so we're getting there. So we start with robotics. Very good. We're doing NILP for the people who knows what it is. And there we go. Maria.
Can I start?
Yes, you can start.
This paper was created with the help of my supervisors, Filipe Alvelos and Karina Pimentel. During these presentations, the following topics will be talked about. I'll start with a brief introduction, followed with the model solving and implementation stages, and then I will end with the conclusion. So, introducing this work. This work was framed within the textile industry, which, as I think you may know, it's a very dynamic and competitive sector, and it is really affected by market fluctuations. At the same time, there has been a growing demand in product customization. So, this sector has been changing from mass productions to smaller orders and more diverse products. And this increased variability is making, especially the scheduling process and the planning processes, way more complex than it was before. For these reasons, data-driven solutions are becoming essential to improve efficiency, responsiveness, and decision-making. As for the challenge itself, this work was carried out in a Portuguese manufacturer of high-end carpets for the international market. This company faced key operational inefficiencies, especially in their scheduling process, because it was fully manual and really dependent on the planner's experience. For these reasons, we created an optimization solution so that it can generate the plans automatically and giving feasible solutions and better ones than the ones created now. So let me begin with a brief overview of the company. This company works in 2 production units. It follows a made-to-order strategy where 70% of their products are catalog models, but that can be customizable by the client, so you can change the color or the materials. And then 30% of their products are fully bespoke pieces created specifically for that client. They have 4 production methods. The unknotted and unwoven. This is a more traditional and manual type of method. And then you have the flat weave and robot tufting. These 2 are automatic. The most important one for the company is the robot tufting, so their main one, because it can make more complex carpets like the one in the picture with complex designs and in a more efficient way. So our scheduling will only focus on this production method. To better understand the operational context, we first mapped the entire process of this robot tufting, from the order placement to the shipping. But for this research, we will focus on the production scheduling part and on the injection phase, because their scheduling only regards the injection phase, because the rest of the production, so the finishing processes, are made in the order in which the product comes out of the injection phase. So the only important part of scheduling will be this specific process. For you to have a better idea of this injection phase, it looks something like this. So you have the base of the carpet, it is stretched into a structure. It needs to have certain dimensions, this structure, and then the robot will automatically inject the yarn based on what they call the vectorization. So there's a vectorization team that will map what the robots, with the movements that they have to make, and he will create the design. So, as the objectives and results, our objective was first to map all of the scheduling process right now, so we can identify the main challenges and some success metrics. And then, based on this analysis, we should develop an optimization model to suggest plans based on the order portfolio and the operational constraints. The expected benefits should be an improvement in efficient use of resources and productivity, while minimizing the manual work, scheduling inefficiencies, and delivery delays. For this work, we used the model-based research methodology in the specific order. So we started with the conceptualization, then the modeling stage, then model solving, and finalizing with the implementation in the real context of the industry. We started this work with our theoretical background of production scheduling, particularly regarding the classification of scheduling problems, different scheduling approaches that could be used, and then some computational efficiency methods so that we can make the model faster. During this review, we also found out that there is a research gap in this area because there are no optimization models in this type of automated production of carpets. Let's move on to the conceptualization. So we mapped the scheduling process as it is right now, and we understand that it is a fully manual, very time-consuming, and dependent on the planner's experience. So the planners will look at the order portfolio, they will allocate it to a robot, and then they will manually see how it fits their schedule. It requires checking a lot of different information, such as backlog, different materials, robot typology, structure selection, and this information is spread out multiple types of data, so it's in different tools. Then we also have the yarn availability that is not always reliable, so they don't always know if the product can go into production if it has yarn or if it's going to arrive or not. Then we have the injection rate estimate. So the injection rate is the meters per hour that it takes to inject each carpet, and it's usually done by the planner's experience. So the planners will look at the design and decide which will be the injection rate, and this makes that the schedule needs to be adjusted a lot of times, because sometimes the product will take longer or shorter time, and they have to adjust the plan. And all of this results in 12% of orders have delivery delays. Going now with the modeling phase. We started the modeling by the data preparation. So we collected different kinds of data, like robot and structured data, and the process manufacturing calendar. So the plant stoppages, vacation, the shift changes. Then we calculated the product duration. So with the injection rate, we can know how long the product will take to produce. And then a key point was we converted all dates to hours. So we calculated a specific date, how many hours has it been since the beginning of the plan, so that we can have a continuous time model. Then we decided to filter some conditions in advance to make the model less complex and with less constraints. So we filtered only unproduced products, only active robots, and only products with some data on yarn availability. So if there's no data in yarn availability, it will not enter this model. And for the same reason, to make the model less complex, we also created data sets with already feasible combinations. For example, we only gave the possibility for the model to choose robots that are compatible with that design. So we didn't do every combination possible. Moving on to the decision variables, these are the main ones that we created. We have X, that is if the product P is assigned to the robot R. Then we have the Y, that is if the product P is assigned to structure S. Then we have the Z, that is the sequence decision variable to decide if the product P is precedes product P line. Then we have the W, that it was a way to manage stoppages. I will explain a little bit better later. And then we have the B, that is also a way to plan the stoppages. Then we have the start time in hours and the end time in hours for each production. Following with the constraints, we have the allocation constraints. That is, if the product is allocated to a feasible robot. Then we have production constraints to make sure that we address the production time, setup times, and the material availability. Then we have constraints for fixed production. So we are able, the planners are able to fix some productions that they want, and for example, fix the first days of the plan, so that the first 24 hours there's no product changing in those hours. Then we have the ones that were harder to model, the stoppage constraints, because we need to ensure that the model takes accountability for the stoppages, and that adds the stoppage time to the production time, because as the product will stay stuck in production for X time, we need to tell that to the model. Then we also have special carpet constraints. Special carpets are the ones that are too big or too small to be produced in a normal way. Too big carpets are produced in 2 times, so they'll do the injection phase, then we'll finish, then we'll come back to the injection phase and finish. And with small carpets, they will be all aggruppated in only one production. And finally, we have the sequencing constraints to make sure that there is no overlapping in the products. As for the objective function, we want to minimize tardiness, but 2 types of tardiness. So we want to minimize major delays. That is when the injection phase ends less than 2 days before the delivery date. And then we have minor delays when the injection stage ends less than 8 days before the delivery date, because they all should end more than 8 days before. Then we also wanted to minimize the make span. So we wanted that the last production of every robot typology could be done way sooner. Then when testing the model, we understood that the model was leaving some gaps in between productions, because here we are only incentivizing for the model to make the last production as soon as possible, but not every production. So we added this last objective function that is to minimize the time between all the materials are ready, so the production is ready to start, and the actual start of the production. Moving on to the model solving. This model was implemented in Python using Pulp with the Gurobi optimizer. During the initial experiments, we observed that the model required a significant time to find a feasible solution. So first we used the Gurobi parameter tuning. So we tested different combinations so that the model would be solved faster. But we found that the gap was maintained, so there was no improvement from a certain time, there was no improvement in the gap. So we tested a second one, that is a warm start. So we gave the model a temporary constraint, that is, we forces the robot to be allocated based on plans that were made before by the model. And then the model found instantly a first solution, and then we took off this temporary constraint. The model went freely, and then it found gap improvements were way more rapid. Then as for results, we took 5 plans created by the company and the similar 5 plans created by the model. And we counted the number of orders that did not have a minor delay or a major delay. And you can see the company's results are in dark green and the model's results are in orange. As we can see, the model performed lower than the company's plans, and this didn't make sense for us. So we started researching and trying to understand why the model did worse. What we found out is that sometimes the planners would have the yarn arrive at a certain date, and they would plan the production before that date. So it was impossible. They could not produce without having the yarn. So we found out that the planners would receive phone calls or emails to say that the yarn would arrive earlier, but they would not put it in the system. So there was no way for the model to know that the yarn was already available. So what we did, and just for a comparison, just as a comparison, because they should always update the data, we created a model with the yarn corrected. So we created the times in which the planners were putting their production, and we said that the yarn was available by then. And then we can show in light green, that our model has clearly an improvement on these points. Of course, that if the yarn are better dates or there was some improvement in data, still our model would perform even better. With those same corrected model, we also measured the mate span, and as you can see, the time that it takes to finish every production is way lower on the model, comparing it to the companies. The implementation. So we extract the data from the company's system, and it goes into an input Excel. This input Excel also serves as a configurator, so they can give different weights to the objective function, and they can fixate different dates. Also, so if they want to fixate a week of production or a specific production, they can do it here. Then we'll input the Excel into the air infrastructure where our model will run, and then it will come out with an output plan. They will then put the output plan into the company system and see it in validation GANs. So this is how they work in a GAN. So we'll put it in the validation GAN so they can validate and pass it through the official one. This was the first implementation we did, but as a future work, we have improvements. So moving on to that. As a future work, we want to gradually increase the automation of the scheduling process. So first, we need to get rid of the Excels. The data should go directly, and we should, when the planners have confidence on our models, we shouldn't have any temporary GANs to validate. They should have trust in our model. Then later, we need to eliminate the model typology assignment, because nowadays they are defining which designs are capable for each models, because there's no way for the model to find out. And then also the treatment of special carpets. So they are the ones right now defining if the carpet is too big or too small. As a conclusion, this scheduling model improved resource utilization and reduced delays. It also enabled progress towards digitalization and data-driven decision-making. Also improved responsiveness to the customer and strengthens its competitiveness in the sector. As a research contribution, this addressed an unexplored area with practical tools and in the real-world context. Thank you so much. And if you have any questions.
Very clear presentation. Thank you very much, Maria. Are there detailed questions over here? The last row is away. Yeah?
Yeah, I have one question. This morning we have a plenary talk that said that only 3% of our research reached the market. Your research clearly has the potential. Did the company already profit from your research?
So
Do you
for
have any plans for that?
yes, I hope so. They want to try to make the planners team smaller and make the plans more efficient. But for now, I don't think they have this implemented, but they don't have it in an automatic way. So only when it is an automatic way, they can fully use this model.
But there is already a big step now, because you said in the beginning to set the environment, the context, that they were doing everything by hand so far.
Yes.
So
So it's already an improvement.
That's a big thing, right?
Yes.
But then we also learned that they can be cheating, because they have information that the system doesn't have.
Yeah.
They are beating Maria. That's not fair comparison. No?
Exactly.
Basically. What I missed a little bit, so this was a kind of last question, is the size of the problem. No? Because how many products are you talking about?
It really depends on the month. So
Uh-huh.
it's a really fluctuating production. Sometimes we had 1,000 products to plan, and sometimes we had 200. So it was a little bit difficult to find a strategy so that the model could find a good solution.
Yeah, because you gave some results, and then I started to wonder, okay, we don't find a feasible solution. It's a very hard problem. Full of binary variables. I think you did a great trick in finding a feasible solution and go on from there. I think so. Great work. Very nice. More questions, guys? More support? We do the wave? The guys in the camera cannot see the wave. So over here, there's hundreds of people over here that are doing the wave. It's amazing. Okay. So thank you very much.
Thank you so much.
And then we are going to the next setting. We have to change the setting now. Yeah. So I'm waking up the technician. Okay. So the next speaker will be Umberto from Coimbra. That's good. You're over here. You're enjoying the weather over here at the coast. Later on, we have Anna also from Coimbra joining us. But Umberto is really enjoying over here. He has to drink the wine and this type of stuff. Very hard. Now the subject of Umberto goes in the direction of estimation. So I already activated some statisticians in the back row that later on will try to kill him. No? So this is,
No,
nah,
it's a good guy.
that is old friends. That's
Yeah.
it's fun. It's not okay. We should critical. We have to be
I will
critical.
try to fill the 20 minutes so there's no spare time.
That's cheating. That's cheating. Find the share. I say 15 minutes, 5 minutes for discussion. Right, so that's it. Nice, thanks. Yeah, we do a control L or something like that, and then it's happening, no?
Control L, probably.
Yeah.
You know how to make it full screen?
I hope so.
Ah, so beautiful. There you go. Umberto, the floor is yours. 50 minutes.
Thank you. Thank you for your presence and thank you for the 1,000 online. I'm sure at least Rui Pascoal should be there. It's one of the co-authors. And the title of this presentation is on the use of range volatility estimators for rough fractional stochastic volatility model. And this is the corollary of a master thesis of the first author, Joana Sender, and the advisors was Rui Pascoal and myself. I will try this, and if I miss this, I will ask for help. It doesn't work. Oh, nice. Okay. I really like this board. So the outline is the following. I will start by motivation, and I will lose all over what I want now. Oh, okay.
We have to find the break.
Yes. One of the goals of financial mathematics is to predict market uncertainty. And one of the important topics to predict is volatility. And because volatility has a key role in risk management, asset pricing, and portfolio optimization, we are addressing this in this work. It has a significant impact during financial crisis, and we have experienced that recently. And advances in modeling volatility clearly improves market dynamics accuracy. A lot of works from academics and practitioners try to capture volatility complexities, but it's a very difficult subject. If it was easy, everybody makes money from the market, but we don't. So, one of the most recent models that tries to capture volatility is rough volatility models. It's a class of stochastic volatility models that are very influential recently in mathematical finance. And they introduced a better way to reproduce empirical features of financial markets, particularly related to volatility in very short time scales. Unlike classical stochastic volatility models that assume that volatility evolves according to relatively smooth diffusion processes, these rough volatility models do not assume that, and they are validated by high-frequency financial data that suggests that volatility paths are much more irregular or rough. That's the notion of rough, and I will try to illustrate that with a picture. The regularity of a stochastic process can be measured by its Earth exponent h, and I will have a formula for that in a minute. And we will try to follow the empirical studies by Gardner et al. That found that financial volatility behaves like a fractional process with a Hurst exponent significantly smaller than 0.5, typically around 0.1. So following this work, we have that, and I will try to skip most of the mathematics because they are very difficult to follow. And we have here a definition of a fractional Brownian motion in terms of Wiener integral. And if we denote WS by the standard Brownian motion, with H, the Earth parameter, we have this formula for a fractional Brownian motion. And it's simply a Gaussian process that is centered, and there's a parameter, H, which is the Earth exponent that is between 0 and 1. If this parameter is exactly equal to 0.5, we have a standard Brownian motion. If it's inferior to 1/2, it is a fractional Brownian motion that is anti-persistent, meaning that the past increments are negatively correlated. And on the other hand, if H is superior to 0.5, it is a persistent process. It is important to acknowledge what is a persistent and an anti-persistent process. And here I have an illustration. An anti-persistent process is a stochastic process in which successive changes tend to reverse direction rather than continue in the same direction. And here we have two simple illustrations. A persistent process keeps the same direction most of the time, not all the time, while anti-persistent changes the direction most of the time. Here it's all the times. So one of the key elements in this study is how to estimate the Hurst exponent h, because if we have h equal to 0.5, we have a standard Brownian motion. That is, we have a memoryless process, a process that is random. If we have h greater than 0.5, we have a persistent process with a positive long-range dependence. And as we suspect and try to prove, if h is inferior to 0.5, we have an anti-persistent process with negative long-range dependence. So the smaller the value of h, the larger or the stronger degree of anti-persistence. And here we have illustrations for fractional Brownian motions with different h parameters, and we can see that when the h parameter decreases, the roughness of the series increases. And if we think about a financial series, it looks much more like this than this. So it's much more difficult to predict. To estimate the Hurst exponent, we need proxies for instantaneous volatility that we cannot directly observe. And for this purpose, most of the studies rely on realized volatility. However, realized volatility requires high or ultra-high frequency data, which is very difficult to obtain and very expensive. What is high or ultra-high frequency data in financial markets? It's data from every 5 minutes or every minute. Okay, and that's very expensive. We cannot, if we try, you can look, we cannot access to that type of data. We need to buy it. Okay? We had a project that was financed by the Portuguese Science Foundation, and most of the money went for Bloomberg to buy data for this type of studies, to acquire high or ultra-high frequency data. So one of the research questions of this work is rough volatility an artifact for high frequency data? And we will try to answer that using low frequency data and see if we achieve the same results obtained by others with high frequency data. And instead of using realized volatility, we use range-based volatility estimators that I will detail very briefly. So range-based estimators are low frequency data that only use daily price information. They use the opening, the closing, the high and the low prices. And if you go online, you can obtain this in any site, in any financial time, in any financial site, you can obtain this information, not the high frequency, not data from every 5 minutes or 1 minute. So only using these 4 points every day, we will try to mimic the work of Gardner et al. That uses high frequency data. There are several range-based estimator. We use this one: Open, Close, Parkinson, Garman and Class, Mellison, and Rogers and Sutstel. Here we have the formulas. I will not detail. I will only emphasize that all these formulas only use the opening, the close, the high, and the low of every trading day. In order to benchmark our results, we also use what most of the authors use to estimate volatility, the realized variance. And there's the formula, but this variance requires that we acquire high frequency data. Okay, we did that only for benchmark purpose. We test our hypothesis considering 9 stock indices, Standard & Poor's and all the rest here, in 15 years, and here is from 2001 to 2016. And this was a specific choice because we want to compare the results with the results of Gatherall et al. We could have more recent data, but in order to compare in a fair way to what Gatherall et al. Did with high frequency data, we use the exact same time frame. And we use this rough volatility model that was proposed by Gatherall et al. To estimate the Earth exponent, that is the parameter that tells us if volatility is rough or not. And we use the exact same model used for high frequency data. In order to estimate the Earth parameter, we need to calculate the Q order moments of a log volatility increment that is defined this way. And with that, and knowing that we need to estimate this using all these estimators, we obtain the following plot of the log M as a function of the log delta, which is the gap. And we see that for all the estimators, the points lie for every of them, more or less, in a straight line. Meaning that, or this implies that, the log volatility increments enjoy this scaling property that was found by Gatherall. So with this, where C is the slope of that line. So using this relation and knowing that we can estimate the slopes for the different Qs, we can estimate the Earth exponent this way, similarly to Gatherall et al. And here we have, for the S&P 500, the different values of H for the different estimators. And we can see that the realized variance has the largest H estimated, while the open to close has the smallest, meaning that roughness increases in that direction. And we can do that for all indices and for all estimators, and we can see that the patterns inside the estimators are similar. And that tells us, and that's the main motivation for computing H, that tells us that, in fact, if you remember that picture for different H's, that tells us that rough is indeed, that volatility is indeed rough. We can also try to find other stylized facts from this rough fractional stochastic volatility. For instance, we can plot the histograms for different legs delta, and we can see that, in fact, it's very close to a centered Gaussian curve, which is also found by Gatherall et al. So the first part of this presentation is to conclude that roughness of volatility is not an artifact for high frequency data, but it's also found when using low frequency data. The second part, and most important, is can we forecast volatility using this model and low frequency data? And this model, and this is difficult formula to digest. This model has two parameters. One is age, that we already know how to estimate, and the other is new. And we can estimate that using an approximation derived by Gabriel et al., and the approximation is this one. The second order momentum is approximately related to new and age in this formula. So knowing age, we can estimate new, and here we have the estimated news for all indices. And with that, we can compute our estimation using that model. And here we have plots of the actual volatility in blue versus the predicted volatility for different estimators. And we can see that, for instance, for open to close, the estimation is not so good. It's improved for Garmin and Class. It's even better for these two. And apparently, the best one is for the realized estimator, the one that uses high frequency data. But one thing is inspecting a plot. Another thing is acknowledging how good is the estimation or the prediction. And for that, we compute a ratio P that compares the mean squared error of our prediction with the approximate variance of the log variance. If you want, this P is similar to statistics to R squared. Okay? It's a proxy. And here we have ratio P for different volatility estimator proxies. And we can see, with no surprise, that realized variance shows the best results for all the markets. And the best range-based estimator is given by Mills. Even knowing that the best results are given by the realized variance, sometimes some of the other low-frequency data obtain very, very close results in terms of precision. So, and the main conclusion is using low-frequency data is not as good in terms of predictions as using high-frequency data, but it's a very good proxy. And most of the times, we cannot afford to have high-frequency data because it's not available or it's very, very expensive. The most inexpensive way to have this data is to start day collecting every 5 minutes or every minute day from all that markets until 10 years, which takes time. We also show that it's not an artifact that volatility is in fact rough. It's rough not only for high frequency data, but also for low frequency data. Among the range-based estimator, which is the main contribution of this work, the open to close is not very good, but some of the others perform really well and can be an alternative to high frequency data. Thank you.
Unless Humberto already said he wants to fill up all the time, and he did 41 slides to provoke that he doesn't have any questions. But I specifically ordered some people to ask questions. So.
I only want to congratulate Humberto for these difficult steps in estimation, and he can optimize estimator. This is optimization, not statistics.
Thank you. I will extend your congratulations to Joana Sendas, which is the student, the master student that successfully concluded the master thesis. Most of this work is hers, so I should congratulate her.
Yeah, but she's watching, no? You said.
Yes.
Okay, very good. So what did you pay to Christina to be so
Not yet, not yet.
Other people want to ask a final question? Then we go to the next. Presenter. That's me for that organized, but that's me. Okay.
So now, Elysius, the floor is yours.
Yeah. What I will do is 1/3 of the slides that Humberto used now. try not to. I'll try not to use all the time. Okay. Hey guys. Let's see where we are. This is Eligius down here. So again, I'm very happy to be here, and there are many friends over here who study this. So it's about Lagrange. You see it?
Did you share the screen?
No. I should change the screen. You change the screen.
Share. Did you
Share with the online viewers.
Oh, okay. Now I need a technician. No, I'm doing elder people stories, so I invite the technician to. So this is a PDF, huh?
Yeah, just the people online so that they can see.
Oh, guys.
Yeah, they can't see right now.
Oh,
No.
guys. Oh, my God. There's 1,000 people that are watching me. There's a lot of pressure over here. So what's the picture you see over here? You see the people I was working with. I already introduced before in the last, I have 13 slides, not 39, not 41, okay? Another typical thing in this slide is that I put a formula here in the middle. It's because Claudia yesterday was very proud to do a plenary session without any formula. So I had to say, this is a beautiful formula, it should be there, no? So what you observe over here is a linear programming problem, and I sketched an application before from battery management, which typically has this shape, okay? Now, basically, we were working on this type of problem before, and the story is that if you use the simplex method, we all know that we are doing matrix factorization, and actually we are working implicitly with an inverse. So it's very elegant. I was sketching to Paula yesterday, that even there's some recent work where we use order one information that's only based on matrix vector multiplication, okay? So this is also a little bit the idea of the augmented Lagrangian. Other motivation of this augmented Lagrangian is that Anna Maria was doing her thesis, supervised by Edith. And Edith was a fan of doing beautiful things with Lagrangians. So she came in this topic, and Pablito was doing his thesis about linear programming. So we're combining a little bit this idea, no? And moreover, Philippe is a big fan of Lagrange, so that we are at the moment we are doing very okay now. Oh, that's beautiful, no? Okay. Is it moving? Ah, that's moving. Yeah. Here you are. You are. Wonderful. Discovering how here that doesn't work very well because now I don't have the complete slide, no? So okay. So one of the motivations of this is what we did in the past was at least let me say it that way. Pablito taught me about working with the simplex method implicitly, where the basis has a deficiency. I mean, you have less basic variables. So I was enjoying that story, but to use this method, we need a feasible solution to start with, okay? So that's what I learned from him, okay? So one of the motivations was that we are having a look at a paper by Julian Hall and his PhD student Yvette by that time, and now they have their own wave of making free available software, which is called HEIS, which can solve things in a very elegant way based on this first order story, okay? So what they were having a look at, they were having a look at how in NEOS the first solution is organized. And this is organized by what is called the idiot crash algorithm. So we were intrigued by that because that algorithm is actually doing augmented Lagrange to find the feasible solution, okay? So this was one of the motivation why for this specific problem, okay, not with the upper bounds, we were having a look at it, no? Okay. So I'm going over here now. But another motivation which we used over here was due to this person, and his name is Boris Polyak. And last year I also heard that he was a winner of the that he was a winner of the Euro medal. Okay, so he was a Russian mathematician, and what you recognize over here, I tried to find an English version of this desperately, but okay. So Boris passed away in 23, I think. But in 22, he wrote a very nice article about mathematicians in the Soviet Union, how was their life by that time. So this was an appreciated mathematician from the high in high. Huh? Okay.
Yeah.
Good. Very good. There we are. So I hope you recognize a little bit the story over here, but what you also recognize over here in the corner, if you focus enough, is the augmented Lagrangian division. This is the quadratic term, and this is the term of the Lagrange. So I'm going to Lagrange now. So okay, going there. There we are. So Lagrange is even older than Lagrange is even older than us. No. This is even 19th century, and the end of the 19th century, this book was published. In the book, there's many things in the book. There's a story about the Lagrange multiplier. So to focus on, I'm always impressed by that. Let's repeat that. So this is 19th century. Okay, Carus Kuhn-Tucker is 1948 for Kuhn and Tucker. Carus is 1939. But this is more than 1.5 centuries after this book. Duality theory is actually coming from that. Now, looking a little bit in this Lagrange, more the Lagrangian story, is that what I show you over here is that we have a linear objective and we have linear constraints in equality form. So this is the typical Lagrangian story. So you take this linear equalities and you're going to put it in the objective. This is a little bit ideal, no? So this is called the famous Lagrangian, and it's beautiful to use a lambda for the Lagrange multipliers in that context, no? So if you rewrite it, this is the focus of the new algorithm, actually, that is now developed recently. We're talking over here about the saddle point. What do I mean with the saddle point? That we're doing a min-max. So, I mean, Lagrange was also on that level. We talked about this saddle point, okay? If you rewrite it now, then I always like this shape over here, is that if you change the min and the max, you cannot always do that, but okay, let's start this story, right? You're maximizing over x a linear term, and you're minimizing over here over lambda, okay? So what's a nice vision over here, if you do not have a feasible solution, this ax is not equal to b, right? So if you were going to minimize over lambda, you get lambda is free, and you get an infinity, okay? So this is the story we have usually, that if one problem doesn't have a feasible solution, the dual has an infinite solution. No? Okay. So this is the Lagrangian story. Now we go later on to the augmented Lagrangian story, where we have the same term, but we add over here a quadratic penalty, right? Okay. So it's written as max, right? Now I recognize this as a convex quadratic program. Actually, a bound constraint for a convex quadratic problem. Okay, this is a maximization. I have some problem with that, so I make it a minimization. From the cup, I go to the cup. Okay, so actually, what we're interested in, if you want to solve this in each iteration, then actually you're interested in solving a convex quadratic problem with bound constraint. Okay. So what we did in the exercises before of the publication last year, let's say it like that, what we did in the algorithm was this phase over here. So Carlos, this is really beautiful, but it's okay. The story of the batteries was easier. Okay, right. If you're going to try to solve this, right, what we did before was using f-min-con, and that's extremely ugly, no? Because I mean, f-min-con, this is a MATLAB optimization for general. Convex, quadratic, convex, even not convex. I mean, nonlinear optimization for any constraint, nonlinear constraint in this type of thing. So this feels very bloated. So that means you have a package that's too big to fit. So one of the obsessions I got last winter was about, can't we do this in another way? Actually, this was already stimulated because Pablito said, let's replace this by some easy projected gradient method, and then it will be solved. And it didn't solve. So we started to ask myself, why doesn't it solve, right? So this came one of my research questions. And my answer is the following, So I'm trying to solve this method and it doesn't solve. You want to find out why it doesn't work, okay? Statement of Hendricks, you can cite me, okay, with that. If the method doesn't work for the small example, it doesn't work for the big one. So I tried to design the smallest example I could. And because I was doing this bloody course on linear programming during 20 years, I invented hundreds of these pictures for each exam where you can do what we call the graphical method now. Okay, so what I have over here, you want to go in the direction of the blue arrow and the feasible set is over here. This line fee is over there, right? So what you do is you take the isoprofit line and you take the last point, which is still in the feasible set. That's the solution, right? Pablito said, how do you know the solution? I see it. It's over there. No? Okay. Then you can also argue a little bit that if the orange arrows are the gradients of the binding constraints, then you have a Kuhn-Tucker story again. So blue arrows in between those. We also wrote down exactly that. Now focus on this. It's the easiest problem I can find. How does the algorithm to solve a quadratic problem solve this? So our first stimulation was a paper of Podiak in 2015 who used the term projected gradient. Now projected gradient is a bit misleading because we are not projecting the gradient. What we're doing is we're doing projected gradient descent. I wanted to stress that. You take a gradient set, okay, go there and then you project. Project in this case means I'm going back to the box, right? I'm going to the bounce constraints. So I'm doing a step over here and I project back to the box. Okay? This was actually the first thing that Pablito wrote down and that didn't work. So I wanted to find out why and how does it work. So if I want to find a feasible solution, that's actually what this Podiak, it's another Podiak, it's a Roman Podiak. Then I have this gradient over here. And after I find a feasible solution, I can go on with another gradient who tries to solve the quadratic problem, okay? How does this work out? Now, here's the picture for you all, okay? I'm still going steady, good. So take the same picture, I'm finding a feasible solution, getting here. Nice, find a feasible solution. So far, so good, right? Now I'm plugging in this solution in the second phase, I have a feasible solution, I'm going to optimize. So what's going to happen? So we're going to do the gradient step and then we project. Gradient step, project. And you see this typical zigzag coming out. Okay? I made a picture with 6 iterations, right? To solve the smallest problem I could design, I need 92 iterations, right? To find a Kuhn-Tucker point of the first Lagrangian quadratic problem, okay? So that feels like, it's not a miracle that it didn't work for the bigger instance, no? I mean, for the small instance, it doesn't work. Where is the pain? The pain is that we have a fixed step size. We're not doing line methods over here, okay? So, very happy to have this result because then I could see it. I have to say that we're the 92 iterations, but I was also cheating a little bit because I didn't put any epsilon like the foot of this morning. Didn't put any epsilon over here. I wanted to have machine precision. No, okay. So this Kuhn-Tucker, which is an easy expression, actually didn't come out up to 92 iterations. Okay. This method, conclusion. This method, don't use it, right? Let's look for other methods. Still have 7 minutes to go, so let's try other methods. Okay, this is the idea. So I'm going to gradient projection. This is something else. It means you project the gradient. okay? And you don't project the gradient descent, you project the gradient. From there, you're going to work. So what the first thing I'm doing is Rosen 9060. Why am I so happy to look at Rosen 9060? Finally, you have a paper that's older than me, than us. No, okay. It's a very old paper. No, okay, good. So Rosen wrote two papers actually in general. You can see that in the handbooks usually. You have to go back. And we have this expression over here, which implicitly says something. Okay, if you take the linear constraints, you're going to project on them. You have basically this formula, which I'm very happy to see because I learned in 1982. No, I was in econometrics, where we are projecting a lot, so it's a beautiful formula. Why do we not like this formula? We don't like this formula in general because I'm doing an inverse. And in the first place, this guy was talking about simplex method, inverse. Let's do first order, okay? So you don't want to do that. Now, in this specific case, I'm doing bound constraints. Bound constraints is very easy. So projection of the gradient is a very easy thing. I don't have to do this formula over there, okay? So the projecting the gradient is very easy. And what I can do, because I'm doing a quadratic function, I can now do what Rosen said. You have to find out if you walk in the direction when you hit your head, no? That's it. Usually in the simplex method, we do the same. You know the maximum step size you can take, no? But moreover, over here, I also have the optimal step size because the optimal step size says when the convex quadratic function has a minimum. Unless it's linear, but then I mean the second derivative wouldn't be positive then, no? I remember it's always I'm doing a convex quadratic, so I have a semi-definite story over here, no? So how does this work out? Everybody is waiting for this moment. The thousands of people are waiting for this moment. How is this working out for the smallest example that Hendrix could invent, okay? So we go to the same picture and say, okay, let's imagine that we start at x0 over here. What is Rosen going to do, okay? So the modified Rosen, if you want, specifically for this case. So it's walking over here to x1, he's calculating, bumping his head, calculating the gradients, walking over here, this is an internal optimum, and he is hitting the corresponding point of the first Lagrange. So I said, nice. So I start with to upgrade my Lagrange story, changing the Lagrange multiplier and the penalty, and I'm walking over here and I'm optimizing. I reach this point, I calculate the gradient, I go here. Over here, I calculate the gradient. Over here, I calculate the gradient. Okay? And so the second iteration of my Lagrange story is going to the optimal point, which was this notorious point over here. That's so far so good. So it looks much nicer than what we have seen before. Okay? That's conclusion. All right? Last iteration for you, right? This is not specific enough in the sense that Rosen didn't write an algorithm for the convex quadratic bounded constraints problem, no? Okay? So I come with another story, which is more scary because the number of rows over here is twice as big as before. And this is due to some ideas that Torraldo made with Morelli in 89, so we're getting closer to where we are now, okay? But my inspiration was a description in the book of Nostal and Wright. I remember Stephen Wright walking around in Lisbon. Very nice time, okay, very nice person. So he's very good in explaining things. Even then, the story is quite difficult. So what's the story about? I'm in a point, I calculate the gradient, but instead of going to the next point, calculate the gradient, I use this gradient to have a trajectory along as far as I can go. Okay, to calculate this trajectory for each component, I have to see when it hits his head. No? Sometimes it doesn't hit the head, right? In this case, yes, because we're in the box. We're pretty certain that we're hitting our. Okay, if GG is 0, if the gradient component is 0, you don't hit your head. You can walk as far as you want. No? So this is a little bit story, right? So you take these guys, you order them, there are duplicates, you add the 0, so it's a complicated story. Now, what we do now is we're going to walk along this trajectory. Okay? So this is what the algorithms do, right? Internally, for each line piece, I'm also doing calculating when is the minimum. Okay? I have the same story over here. Okay? But I have the same gradient all the time. I'm changing the projection as soon as I hit my head, but that's it. Okay? So how does that work out? Now, so the last algorithm I wanted to show you, but okay, it cost me some time to understand it, to write it down. Anna helped me to make it even the pseudocode better. Right? So how does it work? I go from here, I walk over here, right? And then I'm not recalculating the gradient, I'm just following the trajectory over here. There I find out that, okay, I'm at the optimum, I'm at characteristic tick point, okay? From here, I recalculate this notorious gradient, and I'm going over here, okay? From here, I recalculate the gradient, I'm walking in this direction, but I'm doing this piecewise walk without recalculating the gradient, walking over there. So my number of gradient calculations is less than a Rosen. Even the number of points I pass through is less than the Rosen algorithm. No? Does that tell us something? I don't know. I said it doesn't work for the small case, it doesn't work for the big case. No? So this is a little bit the story where it came out. So I need less gradient or fewer gradient steps than a Rosen, and then I'm finding the solution for the small example. Does this work for the big example? I don't know yet. So let's be very silent. Yeah, time is up. Time is up. Very good. So last slide, nearly last slide, because I want the literature also to be there now. Okay. Don't do this predicted gradient descent. That's what I learned from this. No. So this Rosen makes sense. Okay. Because actually we can have the line minimization analytically. No? So that makes it very nice. So this last beautiful algorithm I've shown you, it's more hassle now, so I have to do more calculations, but in the end, for the small example, it works very fine. So this is basically the last slide. I also have the literature over here. I also think I have to be complete with that, where our material was based on and from whom I stole which ideas. So I leave this as the last slide. Thank you for your attention. Is there any question? Paula.
Yes, because you revealed my age, more or less. I'm going to ask
No,
the
because
next question.
after 96, you can also be 1980, no? That's it.
So, first, what happens if you don't have this bound on X with X bar?
I don't know.
A bound, so it seems for.
So I was specifically interested in this bounded problem.
So.
Because you've seen that in the bound is not there in the Polyak Teteriakov paper, the Russian paper, because I mean that's the standard form of linear programming.
And do you plan to make a study on the convergence? Because, I mean, linear programming, you can avoid doing the reverse of matrices, right? You have this revised method of syntax.
Correct.
Where you don't do
No, but that's another methodology. No?
Yeah.
Okay. What was very interesting to me is that this Roman Polyak story, the first one, indeed said something about convergence. And then I realized it's less than linear. So it goes very slow. That it goes very slow is very logical. That's also very fun, right? I think that the book mentioned something, Rosen mentioned something about convergence. I also wrote it down in the paper. It's not in the presentation.
Because to understand what is the real merit of the proposal, right? Because, as I said, linear programming with the revised method.
Sounds more logical,
It has to
huh?
be, it has to be competitive. It says.
Yeah, but I don't
it'd be
compete.
interesting to
No?
know what is
Remember,
the
I don't
budget for-
compete. Otherwise, I would dedicate my life to motorcycle racing and earn more money.
Well,
That
you
was
know
it.
that the syntax method is theoretical. it's not a good method. It
Exactly,
works well in
yeah,
practice, but it's not.
Exactly.
Interior point methods are better
Uh-huh.
for convergence.
Uh-huh. But we've also seen for the application, this interior point method didn't work very well. Why? Because we know that we have a bang process where we just at the boundary, just some some basic variables. The rest is just upper bound or lower bound. Very interesting.
Okay, that was my revenge. Thank you.
Okay. You see, Christina, I didn't pay her to be nice, eh?
But I have one question. The photos of your
Co-authors, no?
yes.
I replaced
They
mine
are
because it's,
very younger.
yeah, that's right. Yeah, the public doesn't use any update of the photo. It's just when he married and then it is live stops. That's correct.
I have two questions. One, you don't need to answer, it's a provocative one. Do you think AI will help you solve the... you don't need to answer.
AI.
And the other one, it's for you to think, in slide number 9,
Yeah.
I like Lagrange too, and I like algebra.
Uh-huh. Oh, sorry.
If you do the math, I think P is equal to 0 in the first row, but you need to do math.
Mhm.
Because if you invert the matrices and compute,
Yeah.
it will become the identity
Correct.
minus the identity. Which is
Yeah. You're correct. This M for this case would be very specific.
okay.
That's what you're saying, huh? Yeah. You're absolutely right.
I am
So this is the generic formula, no, for Rosen. You can find it in the article. It uses the letter M.
and I'll just to teach you, one of the good things of having 41 slides that is you don't stay in the same slide for long for people to pay attention. I'm just joking.
But I had more questions than you see, that's competition. So guys, what we have to do now is we have to go to the virtual part. We have an Anna in Coimbra waiting, so I need assistance over here from
Can I
our
share?
clever. Thank you very much. We're going to switch, Anna. We are going to switch to the virtual mode, so we can all see you are presenting over here. So this, we see your presentation.
Okay.
But
Thank
you're
you.
also estimating, eh? We're estimating, guys. Okay.
So can I start?
Yes, please.
Okay. So thank you. I'll talk about the estimation of risk-neutral density functions from option prices based on entropy methods. This is a joint work with Ana Fernandes and Rui Pascoal, and the result from the master thesis of Ana Fernandes.
We have a lot for Anna's, that's right. Okay. Can you make it bigger?
Okay.
Yeah, they are.
Okay. So
Yes.
I'll start by some introduction and some motivation, and then the methodology that we use. After that, the simulation results and empirical results, and finally, some discussion and conclusions. We consider no arbitrage conditions under arbitrage-based models, which means that the theoretical price of a financial contract, which we call an option contract. It could be a call option or a put option. So this contract is the discounted expected value of its future payoffs under a distribution, and this distribution is we denote by the risk neutral distribution. So we want to estimate this distribution. Why? Because it is very important to pricing new derivatives contracts, or in general for risk management. Option prices are can reveal market expectations since they are forward-looking contracts. So they are important in the estimation of this risk neutral density for the underlying asset. Those prices depend on the price of an underlying asset. So we want to estimate the distribution of the future distribution of this asset. Okay. There are several approaches to estimate this risk neutral density. Some from structural models and others from non-structural models, namely parametric approaches, such as the mixture of densities, mixture of log normals. So we substitute the f function, the density, with a mixture of log normals, or non-parametric approaches, for instance, kernel methods or entropy methods, as we will see. Okay. We measure missing information. So we want to measure, to consider a measure of missing information. So the principle of maximum entropy selects a distribution from limited information when we have some constraints. And the constraints of our problem can be related to the option prices, or market of option prices, or theoretical, so observed option prices, or the moment of the density. We must choose a measure of entropy, and we consider the Shannon entropy, which is applied to the density f. And here the optimization problem considers constraints related to the characteristics of the density. In particular, Bushen and Kelly proposed an optimization problem where the constraints are related to the option prices. So the observed call and put option prices are considered here in the optimization problem in order to estimate the density. However, this problem can bring some ill conditioning. So we have some problems when we try to solve this optimization problem. Another approach from Polis considers as constraints the moments of the distribution, so the mean, the variance, the skewness, and the kurtosis. So it has a lower dimension. However, it's sometimes it is hard to solve when we consider, for instance, the 4 moments of the distribution. So we can move from maximizing the entropy to the cross entropy. which is a measure of the distance between two densities. So we measure the distance of a density from a prior distribution. So our objective function is different now, and we maintain the constraints related to the optimization problem. So this is the minimum cross entropy estimation. Okay. In order, we are going to estimate the density, the risk neutral density, for several days. And we propose here a measure of the difference between the estimates, the day-to-day estimates. So this is a possible measure of the difference that incorporates the maximum entropy and the minimum cross entropy. And it differs if we observe values near 1, we know that we have similar results. However, sometimes that is not observed. So we are going to analyze how this measure works in our data in order to identify changes from day-to-day estimates. In order to evaluate the models, we consider theoretical option prices from Black-Scholes-Merton model and Aston model, and also market data from Microsoft and two indexes, the S&P 500 and the VIX, which is the index of fear. So it measures the volatility associated with, namely, S&P 500 index. Okay, here we have the theoretical formulas for call prices and put prices from Black-Scholes-Merton data. And we perturb, we add some noise to these theoretical prices in order to simulate market imperfections that are observed when we see market prices. So in order to mimic those imperfections when reading market prices. Here we have the estimates for Black-Scholes-Merton data, and we have the theoretical density, which is a log normal density, and the estimates obtained from Bushen and Kelly method and also from Rompolis method. On the left, we have 1 month maturity, and on the right, we have 3 month maturity. So we can observe the results for 3 month maturity are poor, so are not so good when we compare the two estimates, the two plots. Okay, in order to evaluate the results, we can add some error measures, namely the root mean square error and the mean absolute error. However, sometimes we obtain good results when consider these error measures, but the estimated densities are not so good. So it is sometimes it is not, they are not related in the results we can observe. but they are apparently good. It seems to be an accurate pricing because we have low values, better for Butchen and Kelly method than for Rompolis, but they are good. Okay. Another theoretical model is Aston. Here we have two stochastic processes, one for the underlying asset price and the other for the volatility. And we did the same. So we generate option pricing, option prices, and from this model, and we perturb those option prices to simulate those market imperfections. Here we have the estimates, and we have on the left without noise, and on the right with noise. So the results are again poor when we consider the noise. However, this data is more realistic than from Black-Scholes Merton data. Market data includes data from S&P 500, from the VIX, and from Microsoft. And we here, in order to overcome some ill conditioning of the results, we implement a strike selection based on market information, namely based on open interest data, which is a measure of the relevance of each contract, of each option contract. So, considering this information, here we have the estimates for S&P and for 7 days, and we can see some pessimism. In fact, there is negative skewness. So the probability of negative results is higher than for positive results. So it denotes some pessimism. When we look at the VIX results, here the asymmetry is positive. So the right tail here is the most important, since we are estimating the volatility. So it is the index of fear. So we want to estimate the right tail because it can prevent losses. So we are looking at the tail that represents more volatility. And we can observe the differences between VIX and the previous one, the S&P. Also, from Microsoft data, we can observe some negative skewness, so some pessimism for this data. And here we have a comparison between the cross entropy and the maximum entropy for a specific day. And we have here similar results for both approaches for S&P data. So we can observe some difficulties from market data. So we implement, as I said before, the open interest strike selection. So there is data sensitivity, which we try to solve by introducing the strike selection. Also, we present the measure, the new indicator of the risk neutral dynamics, combine the cross entropy with minimum entropy, and it appears to have reliable risk neutral density estimations. Okay, some future work maybe analyze extreme events and longer horizons. Thank you. Thank you.
Thank you very much, Anna. We are getting tight in time. Maybe the switches we made. Does someone want to be reach, or that Anna tells you how to get reach and this type of stuff? Or
I'm sorry, but I can't hear very well.
already standing below the microphone because screaming. And don't worry, Anna. So due to the time, we have to go to the next question. But let
Okay.
me contact you with the question how to get reach from option pricing. Okay.
Oh, I don't know.
Okay.
We try to stop losses. Also, we try to not lose too much.
That's right. Okay. Thank you very much, Anna.
Thank you.
I don't have to do anything. Just us. Okay. Okay, guys, now we're really going far away because we're going to Brazil. The guys just wake up, they are fresh, so they are very happy. They were dancing all the night, but now they're ready. So the difficulty is that they also want to get rich. As you see, we are talking stock market, but about Brazilian stock market. No?
Yeah.
Okay. Are you ready, Lucas?
Yeah.
Oh,
Can you hear me?
yeah, very clear. Thank
Oh,
you
great.
very well. Thank you very much, Lucas. The floor is yours.
Oh, thank you. Good afternoon, everyone, and thank you for being here. My name is Lucas Mieri. I'm from Aeronautic Institute of Technology in Brazil, and we're gonna talk about for to being rich using algorithm, right? So my advisor is Sanderson Oliveira, and we adapted some trading framework here from Brazilian stock market, actually a directional trade framework. So what about this framework? What's the main idea? The basic idea is that most financial analysis sample price based on clocks. So you have a sample that is mostly time dependent. So daily close is value every minute. And that's really convenient. Most of the literature is based on this clock dependent sample, but misses what happens between two samples and spend most of your attention on small fluctuations. There maybe is not so profitable after all. And the directional change paradigm flips this around, and instead of using clock sample, let us size the price of the movement, and the seed is something worth recording. Events only when the price reverse by more than a chose threshold theta. So the representation keeps the movies that matters and filter all the noise. So the phrase to keep in mind is that the reverse is a event because the price move and not because the day pass. So we only sample large movements, so that enough movements to compose our trading strategy, and that's basically a signal filter, right? So it's the same framework. So what's this directional change paradigm? So I think it's defined from a local high, the prices fall. Once falling by a list data, we confirm a downturn. And this is the confirmation point from this paradigm. Everything after this confirmation point is down to the next low, it's overshoots. And the same logic it can be applied in the other direction. So we just sample movements enough to satisfy these theta conditions. So two empirical regularities come out of this, and our strategy rely on them. On average, the overshoot moves about the same amount as the thresholds, and on average lasts at least twice as long as the directional change path. From each bar, also can compute two indicators, OSV and TMV, which measure how far price travel from the confirmation point from the last extreme. And that's the main idea of this type of sample methods. So what we're gonna use this in general. So our starting point is a model proposed by Salman and colleagues this year actually is a multi-strategy thresholds using genetic algorithms. It combines eight directional change strategies across 10 thresholds, which gives 70 sub-strategies and a genetic algorithm, and they choose how much trust in each one of these strategies through a weighting voting system. It performs well on your stock exchange, but we take our benchmark here in Brazil. So why we need to adapt this for Brazilian markets in general? First, is Brazilian market is really volatile. So the volatility level is not even compare some more developed markets. So, for example, the benchmark, the ETF in Brazil, have 1% volatility per day, and Petrobras is one of the largest stock here in Brazil, is nearly 3. So, fixed set of thresholds cannot fit in all of them. And second, the risk-free rate in Brazil is really higher. So it's around 10% a year. It can range for 2 points to 14% over the decade. And that raises a bar a lot for any positive Sharpe ratio you can obtain. And third, to trust the results of this direction chain framework, we can perform a walk forward validation instead of a single split that we found in the literature. So the main contributions is we scale the threshold to each asset volatility. So the framework work everywhere. We're all manual tuning. We add a walk forward validation test, and we recalibrate every fold. We evaluate against the CD, the risk-free in Brazil. That's a really a large rate. And we add a convergence matrix adaptive evolutive strategy, CMAES, as a second option measure. A evolutive strategy that adapts this convergence matrix of many weights, and this is the first time directional change paradigms apply in Brazil on the current literature. We test our four hypotheses, then the ensemble beats the buy and hold approach on the Sharpe ratio matter, and it works as a risk filter, lowering volatility and drawdown for each stock. Um, that's advantage on growing longer training windows, and the CMES generally is better than standard genetic algorithm. We come back to each one of these hypotheses soon. So what is this volatility adaptive thresholds? So the original thresholds on the papers are fixed numbers. Instead, we tie them to each asset to realize volatility on daily basis, sigma, and a space then of 10 logarithmics between tens of 5 sigmas. The log spacing sample lower the threshold more finely, and the directional change events are frequent in lower thresholds. So we can expand this window using many thresholds that can be realized for each stock. So the ensemble aggregation and fitness for the 70 sub-strategies, each one votes just buy, hold, and sell at every bar, at every DC event. We don't use short selling or anything related. We combine them by weighting voting with two rules. If at least three of them want to act, we suspend the hold position. So the real consensus is not drawn out. So and we change the positional only when the buy or sell strictly wins. Otherwise, we keep what we have, which avoid this churning on ties. The fitness optimization is a calendar-based Sharpe ratio measuring returns over the Brazilian risk-free CDI. And one important detail here in Brazil is that the CDI is really high and the transactional cost also really high. It's about 6 times what you can expect on the New York Stock Exchange. And that's impose another challenge for any model that aims to be profitable. So what's our walk forward validation in our model setup? So we evaluate the model on a spending window walk forward, we training every up to every year and test on the next year, which give us ninefold for 30 stocks and in general 270 out of sample folds. And we can do this through all Brazilian stocks, through all discretionary training windows, and you can evaluate multiple times if our model is profitable or not, or if the data is looping bias is the main contributor for our profit. So we expected to have such a large amount of out sample folds to be a proxy of if this model is profitable or not, or if it is better than buy and hold or not, and we can guarantee that no future information leaks in. So that's important. So the first hypothesis we talk about is the cross asset performance. So we have all these folds, and you aggregate the results that are consistent with the first hypothesis. So the CMAS, the matrix correlation approach, in samples reach the Sharpe ratio way greater than buy hold approach. Clearly, that is also dependent on the stock performance. But in general, all the approach, both CME and GA, beats the buy and hold approach in 80% of the cases. And the profit factor is also way larger than the CMES approach. And the mean degradation is a really important metric here that measures how distant the Sharpe ratio is in sample and out of sample performance. So we basically have the half of degradation from the GE approach. So in general, we can generalize better with this model, and we also get a model that is consistent, way profitable than just simple buy and hold strategies. Well, that's a comparison using the Brazilian ETF BOVA 11, Brazilian main equity indices over 9 of the sample years, and the CMAS in sample roughly triple the capital during this investment period, while the buy and hold just double the capital. Notice the CGE rate here is also really high in all this period, and so what we can infer on this is that both approach, both genetic algorithms can get a profitable result of their buy and holding, also reduce the volatility, reduce the expected volatility. And so the volatility reduction we talk about, our second hypothesis, is that every single one of the 2070 folds sit below the diagonals. So the ensemble never rise the volatility related to buy and hold. So we always get a lower volatility, and we also can assure that this reduce the drawdown in lower 95% of the folds. So also the CMA approach have a mean ratio slightly lower and slightly stochastic, slightly lower stochastic than related to GI approach. So in the training window effect, our third hypothesis is about us we giving the model more years to learn from the market patterns. It's the advantage of the buy and hold growth. For about 10 of the sharpening points on the short window, the third with the longest one, the interpretation is that longer windows expose the model to more market regimes, including COVID crisis, and improves in general model calibrations. And now, so on the optimized generalization, we finally get our four hypotheses. when we can compare the two optimizer. First, what degradation means. Again, the degradation means the train sharp means the test sharp is lower. So lower degradation also means that model can improve the generalization in out of sample data. Both optimizer learn essentially on the same out of same shape, but they get really different. The genetic algorithm reaches higher training sharp and then lose about twice as much on the training data, and CMA loses only half as much. So the reason that CMA is built on the search spaces, so a covariance matrix space, adapts this covariance matrix to capture the severity weight related. So the converges to a solution that transfer better in the higher dimensional space and that makes more reliable choice in almost any situation. So the point is we can get this basically the same framework with two distinct algorithms and improve our performance just switching the algorithms to a more consistent and more high dimension space search approach. That's probably the main contribution related to degradation. And in general, degradation not appear in the most of the papers. So we think it's a really interesting feature of the model. So a conclusion also to summarize our hypothesis is to wrap up. Our hypotheses are all consistent when we can observe with the data, which is higher sample data, higher shape or the higher sharp ratio than biholds, lower volatility in every fold, and lower drawdown in 90% of the cases. A large advantage with longer training data, and CMES generalize better than we get actually in the literature using simple generic algorithms. Um, I wanted to read about this model is that this model is a risk filter. It's not an alpha generator by essence. It's like a smart beta approach and works really well on high interest in emerging markets. And the main limitation is that we rebalance once a year. So the model cannot react in the mid-year periods, and it's not explicit sense of the current market regime. So that's exactly what we are going to do next. We try to improve the spend the model using regime conditional weights. So we can weight the model based on the current estimation of the market regime, and the model probably can generalize better on these conditions. So the ensemble can switch this configuration on the fly, so online. So that's it. So I happy to take any question. Thank you all.
Thank you very much, Lucas. To, to be condensed enough in the presentation, actually you introduced many aspects, so you densified in a short presentation. Are there people that want to be rich and have a good question to Lucas over here?
Yeah. Yeah.
I had some curiosity about that you insist on using genetic algorithms for the
Okay.
optimization. So I was just wondering whether we have something in literature of using other optimization techniques for the rate optimization.
Yeah, we find the financial literature in general is really limited about the meta-risk approach. So almost all the literature is based on three or four algorithms like GA, PSO, and this type of algorithm. CMAES is like a state of the art from this genetic or this black box approach, and it's never been used to basically, I think, any trading framework, whatever, whatsoever. So I think the only application of this algorithm is like on portfolio optimization, but not in actually try to sharp generation.
Ah, that's interesting. I didn't know that. So you are very well embedded in literature, at least.
Yeah,
So,
yeah.
uh, Lucas, we thank you, and we're going for a coffee. Some people were already falling asleep, not because of your talk, but because it's warm in the room over here. So enjoy,
Okay.
enjoy your being in Brazil. Okay?
Thank you very much.
Let's go for coffee, guys. If you can say thank you, everybody in the...
Aí é ao contrário. Ok.
Acho que está de sala. Vai ser pouco para o trabalhar.
Francisco, vamos ao conhecimento.
So not everything is in line with the next section. You were wrong.
But still, we will try to keep on time because we need to leave for the white tasting. Are you ready to do the white tasting? Good. We are going for
This is scientific work.
yes.
This is scientific.
Always.
They did the design for experiments of the wine tasting, and
And the major breakthroughs are after.
we are really the rats in this.
I'm going to go tasting, but perhaps I will not be tasting.
Tasting the wine. I'm not going to taste wine.
We're all going to be friendly. So
Carla, gostaste? Eu sei que não, eu sei que não. Tudo bem. Mas olha, há uma boa maneira de vou dar.
Carlos, estou vendo aí?
Carlos, vais seguir a sugestão ou não? Vou? Muito bem. Temos o ti, nem preciso saber qual é.
Hello, good afternoon.
Hello.
I'm the first one presenting in the next section.
Okay, very well.
Yeah, we have the chairman already here.
We are going for a short coffee break and we'll be back, okay?
Okay, don't
You can
worry.
upload your presentations and.
But I have to upload or I can share.
You can share.
Okay.
Okay, in a minute we will be back.
Thank you.
Para usar a sugestão de piscina. Isso para um pouco por se espaço, eu já quero estar. Mais honesto do que isso eu não posso ser. Acho que é só para um sítio qualquer.
eu acho que as pessoas também percebem que cada dia é mais difícil sair e fazer isto, porque cada dia há menos financiamento, o pessoal não quer, não facilitam. Então eu ontem tive de exame de manhã, não me davam autorização para sair se eu tinha alguma coisa.
Olá, Ana Paula, estou-te a ouvir. Olha, eu estou a tentar partilhar, mas acho que não está.
Eu não sei, Adelaide, olha, tens que esperar. Eu estou aqui a fazer o upload daqui para ir ao coffee break. Não te preocupes, vem aí o Humberto, ele já te ajuda. Não te stresses.
Olá, Adelaide. Estás boa?
Olá. Não sei quem é que está a falar, mas...
Tenta adivinhar. Já estragaste tudo.
Tens que falar mais um bocadinho.
Ela não ouviu. Deixa lá. Conhecido, é conhecido.
Conhecido. A última vez que te vi foi no Algarve, no congresso da SPE.
Ah, é o Filipe. Então, tudo bem?
Onde é que estás?
Eu estou no gabinete. Olha,
Ela
mas eu não
está
estou a conseguir
Por acaso não
partilhar.
estamos a ouvir lado nenhum, só ouvimos a tua voz. Isto é um
Não,
bocado
estás a ver, olha,
fantasmagórico.
eu agora perdi-me aqui no meio disto. Que era
Olha, eu
Vou
pus
partilhar
aqui
esta. Ah, partilhar.
Mas eu já vi, não precisas estar
Então,
aqui.
porquê é que não dá?
Não sei, sabes que eu acho que isso tem que te dar autorização.
Sorry. Can you help us?
Pois.
Ah, espera lá. Mostre-me o que estou a partilhar. Ah, eu é que não estava a ver. Vocês estão a ver?
Não,
Eu é
não
que
estamos a ver, nós não estamos a ver nada, Adelaide, porque isto tem que ter aqui uma determinada coisa que nós não sabemos fazer, sabes? Diz o que é que tu
Se calhar é
querias?
só passar. Se calhar é só passar.
A tua está aqui.
Pronto, tem.
Só que a tua estava aqui escondida no X. No símbolo, está bem? Queres que não está bem aqui?
Está muito bem.
Olha, isto aqui não há ponteiro. Tu, Ana Paula, que já fizeste apresentações nisto.
Ai, aos anos já fui para aí há sei lá quanto tempo, achas que eu sei? Não te preocupes, olha, não te stresses, Adelaide, toma um cafezinho, tal como nós, um chá. Olha, eu agora, como é que eu tiro isto daqui para fora sem arrancar a pena, ó Filipe?
Acho que isto é este símbolozinho.
Pois, mas não sai este símbolozinho aqui. Olha, temos pena.
Olha, já tenho aqui até.
Não prova. Adelaide, depois quando ele vier, não te
Está
preocupes.
bem, sim.
Toma um cafezinho.
You know how to put the Zoom because there is the online.
Yeah, it's
Person that is online.
Estás nos a ver? Não. Olha, estamos a ver.
Ah, estão. E a apresentação também? Ou não?
Está perfeita,
Sim.
Adelaide. Agora podes ir tomar um café, esperar um bocadinho.
Faz a primeira, Adelaide.
É.
Estou.
E depois?
E depois é uma outra online. Não sei quem é.
Está
E
presencial, não é?
depois é que és tu. Depois é a Ana Paula.
Eu sou a quarta.
Não, depois és tu, Filipe.
Está bem. Até já, Adelaide.
Tchau, até já.
Vai para a sala.
Está bem.
Hello.
Hello.
So it's about time for us to start this third session of computational optimization and applications. Most of persons in presence are still in coffee break, but I will move on because later on we will have a wine tasting, so we need to keep the schedule. And I will ask, Adelaide is only the second presenter, right?
No, I'm the first one, I think.
Okay, so
Yeah.
Adelaide is already have the slides projected, so you can start whenever you want. Go ahead.
Okay, thank you very much. Good afternoon, everyone. My presentation is about optimization of technical economic evaluation of direct current microgrids with renewable energy sources. It is a joint work with Paulo Silva and José Batista from Universidade de Trás-os-Montes de Alto Douro. First, I will present the motivation for the problem, the optimization model, some technical economic indicators that are used to evaluate the solutions obtained for different case studies. I will describe the case study and the computational results and some conclusions and the future work. The growing use of renewable energy requires efficient and flexible microgrids planning. The DC microgrids integrate photovoltaic systems and wind turbines, as well as energy storage system in an efficient way. So, but it's important to optimize the size. It means to decide how many models, photovoltaic models we should install, or wind turbines, or the batteries also. So the goal is to develop a mixed integer linear programming model to optimize the sizing and the operation of a direct current microgrid, considering renewable generation, photovoltaic generation, and wind generation, storage systems, and the energy exchange with the main grid. The microgrid consists of photovoltaic models, as you can see in this figure, wind turbines, energy storage system. We also know the load profile, and we have a bidirectional DC-AC inverter. The mixed integer linear programming that we will present to find the optimal microgrid size include photovoltaic generation, wind turbines, battery energy storage, also the grid interaction. It means the energy that we buy and we sell to the grid. We consider as time structure, we consider 20 years for the planning horizon. For seasonal representative days, in terms of the demand, for one for each season, and we consider 44 hours per day. I have here the sets and some of the K parameters. We have the D is the set of the days, H the set of the hours, the years. The capacity of the battery is also known. The demand is known. The PV generation is also known for each hour and each day. This generation was computed using the information about the radiation and the temperature. Also, the wind generation is also known, as well as the prices for the energy that we buy to the grid and the energy that we sell to the grid. About the acquisition costs, we have the cost of each photovoltaic model, of the cost of the wind turbines, the inverter, and the batteries. Also, we have the annual maintenance cost for the photovoltaic models, wind turbines, battery and inverter, and this cost depends on the acquisition cost. That is given by, for example, for the photovoltaic model, it is given by 1.5% of the acquisition cost. We consider a degradation of the photovoltaic panels and also the wind turbines that is given by this, and this value as the inflation. As this decision variables, we have decisions about the investment. We have investment decision and grid operations. And as investment decisions, we want to decide the number of solar panels that we will install. That is an integer variable. We also have the number of wind turbines to install, and a binary variable that indicates if the batteries are installed or not. About grid operations, we have a continuous variable representing the energy forecasted from the grid. The energy sold to the grid is in each hour, day, and year. About the batteries, we have the state of charge, we have the charging energy, the discharging energy, the binary variables indicating the charge or discharge in an hour, for a day and a year, and also the quantity, and also we have binary indicators that represent the we buy or sell. Sorry, there is a mistake here. The energy, this is the energy that we charge and discharge. Discharge here already. So the objective function, we want to maximize total profit, which correspond to the revenue that we receive from the energy that we sell to the grid, minus the costs. The costs include the costs of the acquisition cost of the wind turbines, the models, and so on, and also the maintenance costs and the costs of the energy that we have to buy to the grid if we don't have enough. As constraints, we have here the first constraint is the flow conservation constraint, considering the annual degradation of the panels and the wind turbines, ensuring that the energy that we have in each moment is enough. It's enough to fulfill the demand, plus the energy that we sell and that we send to the batteries. We have here constraints about the state of charge of the batteries, considering the capacity of the battery that is a given parameter. We have here the equilibrium of the state of charge, and we also have constraints that relate to the energy that is injected in the battery and the binary variables that are injection or not. In each hour, we cannot inject and charge and discharge the battery, and we have here limits on the energy that we can charge and discharge in each hour that these bounds are given by the characteristics of the batteries that we use. We also relate the energy that is sell and buy to the grid with binary variables, and we cannot buy and sell in the same hour. For the space limitation, we cannot. We can only install 48 models, photovoltaic models, and we have the domain of the variables. As economic indicators, we consider the levelized cost of energy, the net present value, the internal rate of return, and the payback period. And we will consider several case studies, and we compare with these economic indicators. The case study, we consider a microgrid in the Porto region. The solar irradiance, it was obtained from PVGs, wind speed from the IPMA, load profile from redes, energy prices, OME prices. We have here the graph with the load profiles during a day on each season. Here I describe the equipment that we consider. Describe only in terms of the references. Okay. By using the temperature and the solar irradiation, we compute the PV production per panel. Also, we using the wind speed and the power curve of the wind turbines that we use, we compute the wind production during 1 day of each season. So, and we consider we start considering 5 case studies. The first case study, we consider that we don't have no panels, no wind turbines, no batteries. So we have to buy all the energy from the grid for the demand. And so this is the total cost, this value. In the second case, we don't use the batteries. We have as decision variables the number of wind turbines to install and the number of photovoltaic models. And we see that in the optimal solution, no wind turbines will be installed. And we obtain 20,244 euros in savings when compared to the initial cost that we have to pay to fulfill the demand. As we would like to obtain a hybrid system, we impose that we must have at least one wind turbine. And so we get the case study 3. We see that we only install 22 photovoltaic models, one wind turbine, and in this case, there is no, that we have a negative benefit, is a bad choice. But considering, and then we consider the installation of batteries, and we can see that when we consider the batteries, we install more photovoltaic models, 48 models. This is the value of savings when we impose the installation of at least one wind turbine. The savings decrease, but we don't have at least a negative value. We have here a description of the results in this table. We have here the number of models. I already talked, I already said this. And we have here the savings that we have to earn. Okay. We have the levelized cost of energy and net present value. We will see that for case 2, that we only install photovoltaic models and without batteries, is the case with lowest LCOE, case 2. The case 2 and case 4 are the profitable cases with positive NPV. Case 3 and 5 as negative NPV. Case 4 achieves the highest NPV. In case 4, we also install the batteries, so the batteries will be useful to explore at the maximum the microgrid. About the internal rate of return and the payback period, we can see in this table. The payback period for case 2 is 3.14 years. So we can say that in case 2, the case 2 is the best with IRR and the shortest payback. Case 4 with moderate returns. Case 3 and 5 is limited because of the presence of the wind turbines. We can here in this graph we can see the cash flow, and we see that the case 4 is the one that corresponds to the higher accumulated profit. We also make a sensitivity analysis to assess the robustness of the system, and we consider some fluctuation prices in case 4. And if we consider plus 20% on the price of the energy that is sold and is bought from the grid, minus 20% in the cost of energy, minus 20% on PV and the turbine cost, and minus 40% on turbine cost. Cases from 16 to 9. And we will see that only in case 9, only with a reduction of 40% in wind turbines cost, we install wind turbines in the optimal solution. We can see here. We can see that the impact of the energy prices are greater than the impact on the equipment the prices. We have also here the graphs with levelized cost of energy and net present value. So, as conclusions, we consider five microgrid configurations to analyze the impact of integrating photovoltaics models and wind turbines and storage systems. The solution with 24 photovoltaic models offer the best balance between investment and economic return. The solution with 48 models and batteries leads to the highest cumulative profit over the 20 years. The integration of the batteries increase the autonomy and the operational flexibility. The incorporation of the wind turbines, at least for the place that we consider, is not didn't prove to be economically competitive. Um, so the microgrid show with high sensitivity to the fluctuation on the energy prices. The results show that the photovoltaic-based systems are the most attractive solution, while the storage adds value from a long-term perspective. As future work, we would like to evaluate alternative storage technologies, analyze different consumption profiles and climatic conditions, and consider uncertainty in demand and in generation. Thank you.
Thank you, Adelaide. Thank you, Adelaide, for your very nice presentation. We are just 1 minute delayed, so in order to keep up, I will ask if someone have questions to address you in your email, and I will ask the next presenter, Rommel, to set all the things to go to the next presentation. Thank you again, Adelaide. Rommel, if you want, you can share your
Can you let's
and
see.
you can enlarge.
Can you see my presentation?
Yes, it's fine. Go ahead.
Okay. And you can hear me, right? Okay, good.
Yes.
All right, so I'll start. Okay, so good afternoon. Thank you very much for attending my session. So my talk is about some work I've done for evaluating AI generated surrogate optimization algorithms for expensive black box optimization. So basically, as you all know, generative AI tools are now increasingly being used to solve problems. I mean, problems in different fields, including operations research and mathematical optimization. In particular, ChatGPT has been used to formulate problems in engineering optimization. You could use ChatGPT also to formulate some of the standard problems in operations research. You know, in undergraduate classes, I've used it with students. You can use it to develop solution approaches for variants of the shortest path problem and also write Python codes to implement the algorithms. Uh, it's also used to generate a C code for a swarm intelligence algorithm. So in my case, my goal is to explore the capabilities of AI, particularly ChatGPT in this case, in generating codes that implement algorithms for expensive black box optimization. So that's the field I've been working on. So I'm curious, what can AI do? How good is an AI generated algorithm in this area? So expensive simulation-based black box optimization problems are ubiquitous in many engineering applications. So almost anything where there's engineering design or it involves finite element, computational fluid dynamics simulation, they usually involve expensive optimization problems. So there is great demand for algorithms that use surrogate models that approximate the objective function, sometimes also the constraint functions. And the idea is that surrogates are used to guide the selection of subsequent points for function evaluations. And among the most popular surrogate-based methods include Bayesian optimization. So people who work in this area, I'm sure you've heard of this. Also radial basis function methods. So those are two of the most popular methods. And there are commercial and publicly available codes that implement these methods, but they're sometimes only available in one or two of these programming languages. So, for example, the Turbo algorithm, yeah, which is basically an adaptation of Bayesian optimization for high dimensional problems. It's like a local Bayesian optimization algorithm that was written in Python. The Sacobra algorithm, uh, which uses RBF interpolation for constrained black box optimization, was written in R. The stochastic RBF method, that one of the methods I've developed before, was written in MATLAB. It's got variants available through Python, through the Python surrogate optimization toolbox. But again, it's in just in those two languages. Commercial packages such as base op and surrogate op require MATLAB. So in particular, the MATLAB statistics and machine learning toolbox and the global optimization toolbox. So who needs AI generated surrogate optimization codes? Well, if you're a potential user who needs one of these algorithms and you find that it's not available in your preferred language, then you could resort to AI tools to code the algorithm. So in the past, it would be like if I'm working in MATLAB and the code is in Python, then I'll have to find a way to sort of write that code in MATLAB. Or if I'm in MATLAB and I need to work in Python, so basically you have to write the code yourself. But now there's an opportunity to use AI to do that. So, and also other users who need to solve expensive black box optimization problems, who may not be familiar with the literature. So, let's say you're not familiar with Bayesian optimization, all these other algorithms. You might also prompt an AI to generate such a method. So, what can we say about the quality of these AI generated codes that implement algorithms for expensive black box optimization? Uh, so just to keep things simple, so I've limited my study to just generating MATLAB codes using ChatGPT for bound constrained global optimization problems. So I'd like to minimize some expensive objective function, black box objective function, subject only to bound constraints. Um, this can, of course, be extended for other, constraint problems or even multi-objective problems. So the assumptions here is that, just to keep things simple, is that the function is f of x is deterministic. The values come from expensive simulation. One simulation yields the value of f of x for a given input. We don't have gradient information. And for those who have worked in this area, you probably know that the surrogate optimization framework is very simple. Um, it begins with you know initial sample points. So n0 here, we typically need at least d plus one, dimension plus one. I mean, typically, which is the minimum number, d plus one is the minimum number you need to fit a linear model. So choose these initial sample points, evaluate the function at the initial sample points, and then you go through a loop where you fit the surrogate model using data that's available, whatever evaluations you've done, and then you select your next evaluation point, xn plus one, using some strategy. And typically, this involves solving optimizing what's called an acquisition function, at least in the language of Bayesian optimization. So there's a sub problem you have to solve to figure out that next point. And then once you've evaluated that, once you've determined that point, you evaluate the function at that point, and then you iterate. And then at the end of that, once you've consumed your evaluation or function evaluation budget, then you would then pick the best point that you found, and that is your approximate solution. So basically the algorithms just differ on how they generate the next point. So they all have this similar structure. It's basically what kind of acquisition function you're using is where they differ. Also the type of surrogate that's used. So I start with the following prompt. Just to generate one of these codes. Let's say I'm a user who wants to just get started using some code for expensive block box optimization. So here's my prompt. Please provide a MATLAB function that searches for a global minimum point of a computation expensive block box objective function, subject only to bound constraints. Use an algorithm that attempts to find the global minimum using only a relatively small number of objective function evaluations without using gradient of the objective function. So the purpose of saying that is, as you all know, there's lots of heuristics that consume a lot, thousands, hundreds of thousands of function evaluations. We don't want that, basically. So we're clarifying only a small number of function evaluations. So the inputs to the MATLAB function include the objective function to minimize. So I have to be specific what inputs I want, the bounds on the decision variables, the computational budget, and also if using the algorithms and ideas in the literature, please provide proper citations of books or articles. Please also demonstrate how to use this MATLAB function on three very different widely used test functions whose dimensions are 4, 7, and 10. So just to get an entire, like basically wanted to get a running code and demonstrate how it works. So the AI actually generated a fully functioning MATLAB code. It was called BB-op Global Min that implements standard Bayesian optimization with the expected improvement criteria. And that is not a surprise, considering that Bayesian optimization is currently the most popular algorithm for expensive black box optimization. And that particular, the AI criterion is also the classic acquisition function that's introduced in this ego paper a long time ago. Um, but unlike the original ego and other Bayesian optimization codes, the AI generated code simply maximizes the EI criterion over some random candidate points instead of doing a more process. So there are some sort of variations from the original, but essentially it is a fully functioning code for Bayesian optimization. Uh, and then did a follow-up prompt. So let's say I also wanted to see some method that uses RBFs, which is the kind of work I do. Uh, so are you able to provide, so this is the prompt, are you able to provide a similar MATLAB function for computation expensive bound constrained block box global optimization that uses radial basis function circuits instead of Gaussian process circuits? And I think this, and it's just with the Bayesian optimization idea. So basically the idea is that similar in type to that other algorithm. So again, please provide proper citations of books or articles. So what it generated is then a code, another code. It's RBF of global min that uses RBF interpolation and uses ideas from a previous paper that I've worked on that uses what's called a distance-based criterion. Um, what's interesting is that the acquisition function it uses is not the same as the original. It's actually more similar to the lower confidence bound used in Bayesian optimization, except the uncertainty is replaced by a distance-based proxy. So meaning the points farther away from current center are associated with higher uncertainty in the surrogate approximation. So this is sort of somewhat novel, and I think this is sort of accidental. And I think the way it happened is because I say using Bayesian optimization idea, and I think the AI interpreted that to mean mix up, use RVF, but use some ideas from Bayesian optimization, and essentially it created like a hybrid of those two. So it's sort of somewhat novel in that regard because as far as I know, there isn't an actual RVF algorithm that does that, but it is reasonable. You can use that criterion to this LCB similar type LCB criterion to do RVF optimization. So and then there was the AI. Also, at the end of that response, they also offered to generate a code that's closer. So the code said, "Do you want something that's closer to the stochastic RVF algorithm by Regis Shoemaker?" And so I included the prompt. So I basically said, well, yeah, please provide that variant of that code that uses RVF with the same input-output structure. And it generated the code that actually was more similar to that stochastic RVF algorithm, again, with some of its variations. It's not doing the exact code as in the paper, but it's also mixing up some ideas from other sources. So from another algorithm that I've worked on with Professor Shoemaker. It also uses different settings of the default parameters. But again, overall, it is a reasonable algorithm. And in fact, I had to run two variants of it. One was the default one provided by the AI, and I tweaked the default settings a little bit to make it more similar to my original algorithm. And then in addition to that, I also asked it to prompt, so Bayesian optimization yielded poor result, that first algorithm it created on higher dimensional problems. So I prompted the AI to generate a variant of Bayesian optimization that runs more quickly and that's more suitable for high dimensional problems. So can you create a variant that runs more quickly, more suitable for high dimensional problems? And it basically generated a MATLAB implementation of what's now called the Turbo cross-region Bayesian optimization algorithm that's meant for high-dimensional problems. The original Turbo algorithm was written in Python, so the AI-generated code is convenient for users who basically want something in MATLAB. So Turbo employs some kind of a trust region approach with Gaussian process model using the k-nearest sample points from the trust region center. It uses the LCB acquisition function, and I think that's probably where that idea comes from that was mixed with the RVF. The approach is meant to promote local search, which facilitates progress on high dimensional problems. So just to give an idea what it looks like, this is what the actual code generated. One of the codes generated by the AI. It's a good code. It's well documented, very easy to read. It's unlike some of those codes that people distribute where the words are all very close to each other and you can't. It's hard to read. But this is very well documented, easy to read code, and of course you can prompt the AI further to explain some of the steps. Um, I'm gonna skip this in the interest of time because well, I guess I'll give a brief overview of RBFs. More people are familiar with Bayesian optimization. For those unfamiliar with RBFs, I just wanted to show briefly that this is what the RBF model looks like. You basically are fitting a model. So given your data points, you fit a model of this form, which is a linear combination of these basis functions plus typically a linear polynomial tail. Uh, Usually I use a cubic form, but there's other forms you can use for that. The main reason I like this is because it's actually fast. Training is very fast. It can be used for high dimensional problems with hundreds of decision variables, and there's a lot of flexibility for the model that you can use. These are some pictures of what RBF approximation looks like. It's an interpolation model, just like Gaussian process models, except there is that we don't have that statistical model, like uncertainty interpretation, although you could create one that's sort of similar. This is the contour plot of the RBF approximation for the Brownian function. Okay. And so basically in the experiment, I compared the MATLAB codes generated by GPT 5.2 with an original human generated code, my code for the stochastic, I'm just going to call it stochastic RBF for short. It's on 8 well-known test problems, 36-dimensional groundwater applications. It's an environmental engineering application. I chose the stochastic RBF paper because it recently received this Informed Journal Computing Test of Time award. So it was a good algorithm to use for comparison. Each of the AI generated codes were run using default settings, and then the AI generated code. So I tried to do some variation that makes it look more similar to that original code. So these are the test problems I use. These are typical. I could do more, but just to get up, this is a preliminary study. Groundwater is like the largest here with 36 dimensions, although we could go higher. So I run it for 30 trials on each algorithm, 30 trials on each of these problems. Uh, so these are results on the groundwater application. So this is, I guess, my most important among these because it's based on a real application. So the original human generated code is the black one here. It's and the AI generated codes that are similar to that are the blue and the red. And you can see here that the AI generated code actually did better than my original code. So there are some variations it did for that actually sort of improved on this groundwater problem. But again, they're sort of close. So the AI generated RBF codes are here, close to the black one. This was the modified RBF code that uses LCB from Bayesian optimization. For this problem, the Bayesian optimization code by AI didn't work so well. But then again, the original Bayesian optimization code, whether written by a human, usually the for higher dimensional, it has some issues. So I guess this is not surprising. Uh, but for the other test problems, you can see again the black one here. It's actually pretty good. The original was quite good, but the AI generated one was not too far. So the RBF is the blue here is RBF. The purple is Turbo. I should say the AI version of Turbo is the purple one. Again here, black one, good. That's the original, and then you've got the AI generated ones. They're not too far away from the back. So let me just summarize this because of limited time. So bottom line here from my preliminary investigation is that the original stochastic RBF algorithm called MLMS RBF has the best overall performance among the algorithms tested. It on the test synthetic problems actually was the better one. On the groundwater, it was actually sort of, I guess, slightly worse than one of the AI generated codes, but not too far. Um, and then the RBF, this is the AI generated code, RBF of SRBF-B is competitive. So it was best on the groundwater problem, but it was actually quite competitive on the other test problems. Uh, BB of Past is basically a MATLAB version of Turbo. It achieved comparable performance to the stochastic RBF algorithm on some problems. Uh, and the somewhat novel RBF off performs better than this BB off Past on again the groundwater and some of these test problems. So to summarize, so the study compared MATLAB code for surrogate optimization generated by GPT 5.2 with the human-generated MATLAB code, the original one, uh, which is an established RBF method. The codes generated with ChatGPT 5.2 are well organized, well documented. They implement standard surrogate optimization approaches, not exactly the same as the original approaches in the papers, but sort of using ideas that are coming from those papers. GPT 5.2 generated somewhat novel RBF algorithm that was minimizes this lower confidence bound acquisition function that's commonly used in Bayesian optimization. So bottom line here is that the AI generated codes, particular BB off pass and RBF off SRBFB, are achieve comparable performance to the human generated code. On the 36-dimensional groundwater application, it actually performed better than the human generated original stochastic RBF code, while it also the other one, the similar one, achieved comparable performance. So bottom line here is that the results suggest that the AI tools can be used to generate high quality MATLAB codes for surrogate based expensive black box optimization. And so there's great potential for AI tools to assist in developing novel optimization algorithms by combining ideas from multiple methods. So future work, obviously you could use it to generate other infill criteria or other types of acquisition functions, perhaps experiment with those. You can also examine MATLAB codes, AI-generated MATLAB codes for constraint optimization, multi-objective optimization, other variants, and of course use this with other languages such as R or Python. So that's it for now. So thank you so much for your attention. I don't know if you have any questions, but I think we have limited time. So
thank you very much. It's always a nice story to have the human beating AI. Someone with a question?
I have a question, Rommel. I was very happy to be now in your presentation because my name is ICCSA Hendricks. I missed your presentations always, apparently.
Thank you.
The presentation of Don Jones in '97, and Christine was explaining your work in 2008. I was very happy to be there. So I was following the line of reasoning. So what I learned from your exercise now is that ChatGPT was able to recover actually the ideas of your paper. So that's very funny. Just one curiosity, driving curiosity. So what does ChatGPT suggest for the optimization of the acquisition function? Because it's generating the MATLAB code, but how is it optimizing the acquisition function?
I think it's basically. I did only. I guess it's a preliminary study, so it was just using ideas that other people are already using. But I think when prompted, you could actually ask it to do other ways of solving the acquisition function, meaning optimizing, either creating a new acquisition function or even optimizing. I think there's great potential that I guess we just need time to sort of sort it out, experiment here and there. As you might have heard, AI tools have now been used to solve open problems, in mathematics that people haven't been able to solve in like decades. So it's not surprising that even in the field of algorithms, if we're developing algorithms, we should be able to experiment with new things that we haven't even considered or that we thought might be too difficult. But then with the assistance of AI, we could probably try out new things. So for now, I think like I said, it was mainly it's more like a passive. I think my approach is more passive, but I think you could do a more active one where you could actually sort of work with an AI like a collaborator. I think that there's great potential for that.
Yeah. Possibilities. Okay, we
Thank
should
you.
stop here. So
Yeah, we are behind time. Thanks again, Rommel.
Thank you.
And we move on to the next presentation by Philippe.
Presents.
No pressure, but we are 3 minutes delayed.
No pressure.
No
No
pressure.
pressure at all, and we want to go to wine tasting really on.
Yes.
So, hello everyone. My name is Philippe Alvelos. I'm
second author there. I'm from here, from the University of Munich. And I will present a joint work with the other mentioned persons there about wildfire fighting, namely prepositioning wildfire resources for attack wildfire. In this presentation, I'll start by motivating the theme, wildfire, and how, why it is important. I think it's not very difficult to motivate this subject.
Sorry,
But still,
just one thing. We need to share it online. Sorry.
Okay.
Sorry.
I can come. I can.
You can keep from.
Okay. So it's not difficult to motivate the wildfire subject.
Thank you.
But I will start by that, and also to give some context for the work that we are doing now. And then I'll talk about deterministic optimization models for fire suppression. And now I will introduce uncertainty and a slightly different problem, which is the prepositioning one. I will talk a little bit about the method that we use, which is distributional robust optimization, and it's particularly interesting for this type of problems. And also some computational experiments, and at the end I'll draw some conclusions. So in Portugal, we have this set number of fatalities. In particular, we had in 2017 a very high number of deaths resulting for very big fires. Well, during the years, there's in most of the years, there has been some fatalities. But of course, there are also other factors that are important in wildfires, as the economic environment issues and so on. Just to give you some more numbers about wildfires in Portugal, what you see on the map on the left is the area that burned from 1 January 2025 to 31 August in the same year. These dark spots or regions are the burned areas, which correspond more or less to 3% of the national territory. So it's a very big area that is burned every year. Very important. In Portugal, it has been made a strong effort to contain the number of ignitions, but it's not so easy to contain the area that burns. Okay, so here you can see that this is the number of ignitions. In the last years, it's most of them it's not very high, but the area that burned is.
You cannot touch the screen.
Okay, sorry.
Oh.
Okay, we are now involved in a project called FireSys, and the idea is to take a platform that already exists, that gathers information for different types of sensors, as you can see here, from drones, from equipment in the firefighters, and so on. And for instance, from meteorological stations, in real time, the direction of the wind and the intensity, and so on. And we'll have, the team that is working with that part, that informatics part and sensors part, already has that system working for other type of problems. And what we are doing is to use that system to first to include fire modeling. So what the information required to fire modeling as fuels, wind, and stuff like that. And then our part, so this is as a fire team, software team, and our part is the optimization. So it's this line here. How should we move resources to manage fire, to try to suppress fire, or at least in a general sense to manage fire. Now focusing in optimization, since the early 1960s, models, operation research models that fall like that were used or start being used there. In recent years, there have been lots of work on this, in particular on fuel management and fire suppression. I just mentioned fire suppression. There are some references that are more related to this work. Different approaches. I'm not going to details, but there are many approaches, and some of them very different. What we are trying to do here is to develop an efficient approach for initial attack. Initial attack is when the fire is detected during some period. We make some effort to contain fire during a small period. And if it's not contained during that small period, for instance, in Portugal, it goes up to 90 minutes, then there is a judgment of this current situation, and then an extended attack begins, which may involve more means, more resources, and so on. Okay, so our approach here is for an initial attack. We detect an ignition or we detect some fire perimeter somewhere, and we'll try to send the resources there to contain fire as early as possible. Okay, what we are doing here, and it is not so common, it's to integrate fire spread and optimization in the same model. So we are not dealing something like optimization simulation, which is we simulate fire, then optimize, and then simulate fire again. We are not doing that. We are just having one mixed integer programming model. And inside the mixed integer programming, as I'll show you later, inside the mixed integer programming, we'll have this fire spread and the definition of the attack positions, the optimal attack positions. And we will do this with uncertainty. So this is quite elegant and is the basis for all these approaches. And the principal idea is this principle, the minimum travel time, which basically states that if we have a landscape and we represent that landscape as a network, and we associate fire transmission times between the nodes, we can find the paths that the fire will follow if we use shortest paths algorithms. So for instance here, we have a landscape here. If we have a set of ignitions in this corner, if we have the fire transmission times in the arcs, then applying Dijkstra, we'll get the fire paths, and beyond the fire paths, we also have the fire arrival times.
That also depends on the wind direction, no?
The wind direction is implicit in the fire transmission at the arc.
So it can differ, no?
Yes, you can have, for instance, in this arc, if the... Sorry. Okay, cool. Yeah. If in this arc, if the wind is aligned with that direction of the arc, then the fire transmission will be smaller. If the wind is not aligned with that fire transmission, with that arc, then the fire transmission time will be higher. Okay, I'll give you a small example in the next slide. Let's see. Okay, so this is the main idea. And what we are doing, because we want to have some realistic data, what we are doing is to, here we're using the same intensity in all the landscape, but not necessarily the same direction. And what we are doing is to use real full models for Portugal, and we also using the topological aspects as slope, and we are also use the wind. So we can determine these fire transmission times or estimate these fire transmission times that I mentioned in each arc using these inputs. Well, there are a lot. This is another area of research, but we are managing to do this. Okay, just to give you clicking hands. No. Yeah. Okay, just to give you an idea of how it works in algorithmic terms, then I'll show you the bigger images. What you have here is two networks, the fire network that is the same that I showed you before, but here we have different colors to correspond for different flow models, different flows in each node. And we have here some values that you don't see, but are the fire transmission arcs in each direction, because it's not symmetrical. And here we have a resource network. So this is the fire network, this is the resource network. We are assuming that we have our resources are in the yellow node, and they can travel in this network, which has for each arc a time travel, the time that it takes to travel in that arc. Okay. In this case, they overlap, but it's not necessarily like that, as I showed them. So what we want is an example on the left. We have an ignition here. We have our resources here. So the fire starts spreading in this direction according to the arcs. We don't know previously what will be the direction. It depends shortlist files. It will go through these nodes, and our resources will go trying to meet fire. In this example, with 4 resources, you can stop fire there. All the green nodes are safe. Okay? This done with mixed integer programming. It was not looking at it and choosing the colors. Okay. Now on the left we only have. Come again?
That's good.
Okay. On the left we only have 2 resources, so we don't have so many helicopters or so many crews, terrestrial crews. We only have 2 resources, and so we cannot stop the fire here. We have to stop the fire here, and the burn area will be higher. Okay? This will be 2 different instances because we are fixing the number of available resources in our instances. Okay, I'm taking too much time in this part, but I think it's important. The main ideas are these. This is well, I'll start with the model, but I will not go into too many details. But this is just a representation that we are doing for real landscapes. This is Baião. No, this is Ponte de Lima. So it's here in Minho, in this region of Portugal. And what we have is this is the fire, as you can see, the fire network related with the fuel, and this is the resources network. So you have vehicles, ground vehicles that can travel on this. This is from OpenStreetMap. And what we have to do, since the networks are pretty different, right? The networks, fire network and resource network are pretty different. Nodes are not on the same place. What we have to do is to define a cover. Each resource node can cover a given set of fire nodes. And this is what it represents here, different types of resources. And we can, for instance, when you put a resource here, all these nodes will be extinguished. Fire on all those nodes will be extinguished. These are more a couple of slides with this. So, for instance, here, there is an ignition here. These curves are isopronous. So all the points in the same curve have the same time. Fire arrives at the same time there. And we have our resources are here, and they move like this to try to contain fire. Here they don't contain fire, but it will escape from here. Here our resources contain fire. And okay, so this is also a very elegant model that combines fire spread and resources utilization. The T's are for fire spread, so we have decision variables that in an optimal solution or in a solution will give the fire arrival time at each node. And the Z's are for resources that will give us the movement that the resource should do. From K to L, resource R is equal to 1 if it moves from K to L. In this deterministic version, K is fixed, is where the resource is. Okay, entering the uncertainty, what happens in reality is that we don't know, or if we want to use this type of approach, before an ignition occurs, we have uncertainty because we have our resources, but we don't know where the ignition will occur or what direction the wind will take. So what we can do, and it's called preposition, and firefighters do this usually, in particular in the summer in Portugal. What we do is to preposition our resources. So instead of having resources in a fixed place, we decide where the resources should be, taking into account the risk map for the fire for that reason. So, and then what we are doing here is that we have a set of scenarios. These are just 3 scenarios with different locations for ignitions and different winds. We have a set of scenarios, and we have a set of positions where our resources can be based. And with that, we get a 2-stage optimization problem. In the first stage, we decide the position of the resources. In the second stage, once the scenario is revealed, once the ignition and the wind direction are revealed, then we'll move our resources to that scenario. This is typical two-stage problem. Well, we have the second stage variables associated with the scenarios, omega, and so on. Two usual approaches for this type of problem is stochastic programming, which is based on defining one probability for each scenario. Other possibility is robust optimization, in which you don't have probabilities, but just look at the worst case scenario. So the optimal solution is the one that has a better worst case scenario. And what we've done here was to use distributional robust optimization that takes the other two as a special cases. So this approach can be, if simplified, can be used as stochastic programming or robust optimization. And the idea is that we have a set of scenarios, but we don't have probabilities associated with that set of scenarios. The probabilities to be considered are the ones that are the worst case for the solution. So what we have here is a set. This omega is the scenario. This phi is the probability of. This is the probability distribution for the scenarios, and what we are trying to do is to choose the scenario that, in the worst case of the probability distribution, is the best one. For that, we need to define some measure of distance of scenarios, and the ambiguity set that we use is the Kantorovich that is related with when we have a solution, then we will see what is the worst distribution probability of the scenarios for that solution. And that is the way that we evaluate the solution. And then we have an algorithm that basically starts with a few scenarios, optimizes, find a solution. When I say a solution, is the first stage solution, a position for each resource, then solves a subproblem, then computes for all scenarios the value of that solution, and then solves a subproblem that defines the worst probability for that solution. We did some computational tests. Well, that's the Bayern region here. The test. I had the idea that was Pontlimo, but perhaps it's Bayern or the image is different from here. But well, we have here the characteristics of the setting of our computational experiments. We use the Rothermel-Fires behavior model, which is the most used ones for fire spread. And we did use the 90 minutes. Well, we decided 30 minutes is for the alert. So we assumed that there was an ignition, and after 30 minutes, the ignition was detected, the fire was visible. And then we have 90 minutes to try to contain the fire. And we have these instances with 3 different number of ignitions, 3 different numbers of resources, and 80 scenarios defined by the wind directions and the ignitions. For one ignition, the problem is really easy to solve. In all cases, only one iteration, only a generation of scenarios for one time was enough. With 2 ignitions, it was a little bit harder. And in particular, when we have 4 ignitions, there are some problems that are particularly difficult to solve. Here, for instance, we have 4 ignitions, 3 resources. This epsilon is the distance or the size, the distance of the scenarios from the nominal one. And this is the number of burn nodes, the number of scenarios that were generated, and the computational time in seconds, and the number of iterations that we do. So these are clearly the most difficult instances. In any case, we had solved all instances to optimality, relatively in few iterations in general, and with reasonable solution times. In particular, to decide prepositional locations, it's not an online problem or a real-time problem. So we can decide the day before or during the night where to locate the preposition. So the time is not so much relevant issue. Of course, it's always relevant. And an interesting result is that few scenarios are needed to define the optimal solution. So I presented this optimization approach for prepositioning firefighting resources. This method is particularly suitable because it allows to, well, in this worst case scenarios are very important in firefighting, obviously. So this is somehow, but maybe it's too conservative just to choose the worst case scenario. So this allows to a balance between the worst case scenario approach and we can put some stochasticity in the approach. So it's particularly interesting. And well, we believe we have some strong potential for using this in realistic problems, in particular because we can increase something important here is the resolution of the network. And here the resolution was not particularly low, so we can improve the resolution and have with these results we can still improve the resolution to have more effective modeling of this type of problems. Thank you for your attention.
Thank you. We are behind schedule, so if you have any questions, you can try to find Philippe in Gala dinner and try to schedule a place in his table. Thank you.
It's a very nice story.
Yes, and important.
Ready for a bigger presentation.
Yeah.
So we move to the next presentation, and I will ask for.
Shortness.
No.
I will try. I don't promise.
To spend your 20 minutes. Well, if it's short.
But I had time here, so.
Okay.
I think I'll need my phone because otherwise I won't be able to control the time. Perhaps. So.
Did you share your presentation? No,
Nope.
but someone will help you.
Well, I'll try to see if I'll think I can do it. I think. Where do you need... Okay, you can come and go back to my phone.
It's easier. Yes.
Thank you. Well, my name is Ana Paula Teixeira, and the title of my presentation is the convergence analysis of a one-norm neighborhood Mehrota type algorithm, and this was a joint work with my colleague Regina de Almeida from the University of Trás-os-Montes e Alto Douro. Well, what we want to prove in this work is that the algorithm, the version of the algorithm that we are analyzing, that's Merotra's predictor corrector interior point method variant, initially proposed by Bastos and Paixão, and now we are using the one norm neighborhood, is polynomial. She sees that it terminates in a number of iterations of the order of at most n up to 1.5 log epsilon iterations. And we also prove that this algorithm is k-linear convergent. Well, I'll begin by briefly presentation the problem and some notation. Here we deal with, in this work, we deal with primal dual pair of linear programming problems in the standard formulation, where we want to optimize the linear function subject to linear constraints. A is an m by n real matrix. C and B are real vectors, and X, B, and U are variables. We define X as the feasible set of the primal dual pair of feasible solutions that are the solutions that satisfy the constraints of the primal and dual problems. When considering just the positive X and V solutions with the X and V positive, we get the strictly feasible solution set, and we work in this algorithm with the norm one neighborhood. we have also works where we use the two norm neighborhood and infinity norm neighborhood. And in the literature, there are not many works that use the one norm neighborhood. Well, I'll talk a little bit about the motivation of analyzing this neighborhood. And the fact is that the most common neighborhood used in these methods is the two norm neighborhood, but this neighborhood is a very restrictive neighborhood, and it makes the algorithm quite conservative because it obliges the iterates to remain very near of the central path. So even when this condition is not needed in terms of feasibility. So the algorithm takes much more iterations than it would be necessary. Initially, we analyze this algorithm with two norm neighborhood, and then seeing that, we decided to study what happened when we changed to the infinity norm neighborhood. That is a much more flexible neighborhood that allows to go further in the predicted direction, the affine direction. But the problem is that by using the infinity norm neighborhood, sometimes the algorithm loses the control, and you need a very strict correction towards the central path. Well, so we decided to see what happened when we use a neighborhood that could get the better place of these two neighborhoods. The one norm neighborhood allows to take advantages of the flexibility of the search in the affine direction, but it also allows to have corrections less aggressive. Well, that's the motivation of doing this analysis. Well, this is a Mercator predictor corrector algorithm. So we have an affine direction, a predictor direction that is the triple that satisfies this first linear system of equations, and the corrector direction is one that satisfies the system number 2. Well. The gap between the objective functions of both primal and dual problems is measured by mu and is given by this system, 3 system condition. And it is also important to present or to deal in the proofs that I'm not going to do the proofs. So, but if you want, I can.
You can read the paper.
Yeah, no.
Because we don't do the blackboard, otherwise you could follow it.
But I think it's also important to note that we have to focus our attention in the indexes of inner product of the affine direction that are distinguished between the indexes that have this product positive and negative. Well, the algorithm, we also need to find the maximum step length that allows that in all iterations to maintain the iterate in the iterates positive. And so we compute the maximum step length for the primal and dual problems. In order to keep the next iterates away from the border of the region, we only take 99.95% of the step length in the real in the algorithm. For this theoretical study, we consider the minimum step length between the primal and dual, and we work with that unique value. So the algorithm can be summarized in this structure here. So we begin with an initial point in the interior of the one norm neighborhood. Then, while our termination criteria isn't satisfied, while the gap isn't reduced enough, we compute the gap, we compute the primal, the predictor and corrector directions, the step length primal and dual, and then we actualize the iterate. Well, now we'll talk about the convergence analysis. Our analysis main results are two, and we called it theorem 1 and theorem 2. But to arrive there, we need some other results. Some of them were derived by us and others were already in the literature. But in order to maintain the work self-contained, we decided to present them. Well, our first result, lemma 1, is allow us to obtain an upper bound. It was derived by us and allowed us to obtain an upper bound for the nonlinear term of the predictor direction. Lemma 2 was already in the literature and also finds an upper bound, but for the norm 2 of the componentwise products of the two vectors U and V in terms of the sum of those two vectors. I present these results here because we need these results to derive this other one that is very important to obtain our first result, theorem 1. And this other result that we derived, and it's important for our theorem, allow us to obtain an upper bound for the one norm of the nonlinear term of our corrected direction. Well, to arrive to our first main result, we need the first result that I presented, lemma 1. We need proposition 1 that I talked now, and we also need this other result. This other result, named lemma 3, presents a relation of the duality measure of the next, related to the next step, the relation between the next duality measure and the current duality measure, or duality measure concerning the actual iterate. Joining first result, the previous proposition, and this result, lemma 3, we arrive to our first main result. And this main result says that if I have my current point in the one norm neighborhood, and if I have a predictor direction and a corrector direction computed by the formula that I previously mentioned, then the maximum step length that I can take in order to have the guarantee that the next iterate is still in that neighborhood has an upper bound that is this quantity here. So I need this quantity here in order to prove that my algorithm has polynomial complexity and the order of that complexity. Okay, so this result here, jointly with my previous lemma that relates the actual duality gap with the next duality gap, and the next result will be the three major points for proving that goal, okay? That algorithm has polynomial complexity, and that is the order of complexity n up to 1 point log epsilon. Well, so what's the piece missing? So we have the upper bound of the maximum step length that you can take. We have the relation between the current and the next duality gap, and now we need this. This is the proof, but I'll skip it. If you are interested afterwards, I can show you. And we have the last piece necessary to the final result in terms of complexity. This is another result that was already in the literature, but what does it say? It says that if I begin my algorithm with an initial iterate here satisfying this condition here in terms of gap. Okay, and if in each iteration of the algorithm by solving when solving Carrosh conditions, I reduce the gap by this factor here, a factor of this form, 1 minus gamma divided by n up something, where delta and w are positive constant numbers, I have the certainty that a solution will be found by my algorithm in a number of iterations no higher than this amount here, n up w log epsilon. Okay, so joining this result with the maximum step length that I found in the theorem line and the relation between the gap current and next one, we derived our last result that guarantees that our algorithm, in fact, stops with a solution in a number of iterations no larger than n up to 1.5 log epsilon. Okay, and I only show you briefly. This is it's simple. So we join the relation lemma 3 where we compare and find a relation between the current and next gap by, of course, doing some calculations. We consider the aqui. Fiz para aqui qualquer coisa, ó. Eu cliquei para aqui em qualquer coisa e isto encolheu. Mas pronto.
Try and put in the previous page and again. Control L.
Control L?
Yep.
There you are.
Okay, thank you.
And then go there and just click hide.
Hide. Not that one.
Next one.
Hide, okay. Mixing those three results, the step length, maximum step length, lemma 3 comparing the next relative gap with the current one, and the previous result, where I effectively get that reduction factor here, okay, 1 minus delta and so on, delta. Then we have the guarantee that our algorithm terminates with using the one norm neighborhood, terminates in a number of iterations of the order of n up to 1.5 log epsilon, okay? And by doing this, and as this factor is less than 1, we conclude that not only our algorithm has polynomial complexity, but it converges with k-linear rate. Okay? And that's it. I don't know what's time, but
Thank you so much. And thank you for
I think
being strict
I
with
was
the time. Yeah, it's very nice. Even knowing that it was a huge effort, we are still behind time. So we can ask questions during
The wine taste.
the wine taste.
Okay.
Wine taste.
Yes. So we move on to the last presenter, which is Karina.
We have a special sporting team up here. Into the wave if you want.
Close all tabs. Yes. Okay. Try to put this here. Just a second. No. I need to put it there. I don't have a mouse here. No. Okay, maybe I can put it
Here in the desktop. Save. It is Filipe Alvelos. No, not this one. Cancel. Sim.
Porque eu estava querendo sobrescrever isso, talvez seja
Okay, let me try to do this. Here we go. And that's it. How do we share? Can you help us sharing? That's not my part. To share in the... We have someone expert in this.
Go ahead.
Well, I guess I have the hardest job here to keep it shorter.
Yeah.
But I will try. Feel free to interrupt me if I'm
No, go
running
ahead. Go
late. Yeah.
But you're an expert. You do your thing fast.
Yes. So again, nice to meet you. Thank you so much for being here. I know this is the last presentation. It's super hard sometimes. My name is Karina Andreata from Federal University of Espírito Santo in Brazil. Myself, Maria Cláudia Silva Boeres, together with Renato Elias Nunes, we developed this book called A Reinforcement Learning Guide, General Variable Neighborhood Search for the Traveling Salesman Problem. So I'm going to present here just a briefly summary about the topics we are going to cover today. So motivation, contributions of real algorithms that we developed throughout this work, reinforcement learning approach, the reward function as usual, experimental setup, results, performance, and so on. So the motivation, everybody knows traveling salesman problem within optimization field. I know, so I'm not going to explain this type of problem, but this is basically an hot problem, and we know that exact algorithm sometimes takes longer than we expected to present us a good solution, even the best known solution. And this motivates, of course, method-based approach, such as the GVNS that I just mentioned. So the problem is that the classical GVNS sometimes only relies on fixed operator ordering, as you can see over here. So we have this fixed operator ordering, meaning we have a predetermined sequence to operate our local search within the VNS, which stands for Variable Neighborhood Search, meaning we have a very rigid manner to operate our local search. GVNS is basically a variant from the VNS, which consists on a VNS with a VND, which is an algorithm that executes many types of local search instead of one operator. So our idea here is to replace this type of VND by using a reinforcement learning approach. So this is the main idea. And motivation, we have a lot of motivation that I'm not going to talk about every single topic that we have here to prove that our work is valuable in terms of motivation. But one of them is the lack of work related to VNS combined with machine learning approach, AI approach, reinforcement learning, and so on and so forth. And also GVNS, this type of trajectory-based approach, they are very largely used in this type of problems such as TSP and so on. The contributions overview here, I have three pillars in my work, in our work. So first of all, we know that we need to initialize our solution to present to our algorithm a solution that is close enough to our best known solution and that helps guide our search space in a better way than greedy heuristic algorithms. The second pillar is the shaping procedure. The shaping procedure is largely using in VNS, GVNS, in its variants. But we found out that adaptive shaping procedures are very rare in literature speaking. And that's the reason why we explored 3 pillars related to adaptive components. Within the initialization phase, within the shaping phase, which is the diversification piece of things, and finally, within the intensification piece of an algorithm or methodistic. This is the contribution overview. So here I am presenting to you basically the pseudocode, which consolidates the 3 pillars that I mentioned. So initial phase, initial solution, construction, the shape method, and then the reinforcement learning local search method as well. So at each iteration, as you can see, I have a level of shaping of perturbation. So with that perturbed solution, I'm going to have this solution from the shaping of the cost. And with that solution, I'm going to intensify my search with the reinforcement learning. So this is the idea. It's very simple. Now we are going to focus on the initial initialization mainly. So I mentioned that we implemented an algorithm called multi-agent reinforcement learning. It's a bit complex to explain everything, concepts and everything within 20 minutes, but the idea here is just we are constructing tours using reinforcement learning into learning algorithm. It's just this is the overall idea. So we start by constructing different tools. The agent is a concept from reinforcement learning. The agent will observe the environment. It will select the action. So imagine I am a robot and I am observing my environment. So my state will be, in that case, the city chosen, and my action will be the next city to be chosen in this process. So I am basically constructing my tour step by step while I am learning with my Q learning algorithm. This is an online process of getting knowledge with the time. So this
your state is the partial tour.
My state is my previously city in my tour. So I am at this city right now, and I'm looking to the next. Yes, exactly. So this is basically a multi-agent because I am constructing 5 tours in that case at the same time. So I have 5 agents constructing different tours. This is the main idea. Let me see the time. Okay. So the shaping process that I mentioned, that I just mentioned, it has an adaptive component because mainly most of the shaping process, we only have for each type of key type of level, we have just one type of operator. For example, 2 OPT, operator 3 OPT. So we have just one type of operator, and it's rigid again. This is rigid, and my algorithm cannot adapt with the time these possibilities within a certain key. Our idea here is to introduce a level of strength, let's say, when I am increasing my level of neighborhood. So this is mainly to escape the local optimum and to add another component, another adaptive component in our algorithm. And we observed in our experiments, in our results, that our implementation, our basic implementation was too strong that the reinforcement learning improved just a little bit when we added the local search as well, because this adaptive shaping procedure helped the algorithm to be strong enough to fill the gaps in the literature that we found out. And finally, this is the reinforcement learning local search that I'm going to try to explain really quickly. Different from the more, the multi-agent reinforcement learning, this one, this is an operator transition instead of city transition. So I am at one city right now, and I'm looking to another city to select based on a specific policy. Right now, I sit on an operator, and I click on the screen again, and I just select everything I think.
If you go back and forth, yeah.
No problem. It's visible. So, okay. And then I am sitting on a specific operator right now, and my policy, which is epsilon greedy policy, this is going to determine my next operator. So imagine I am performing the two OPT operator, and now my policy just provided to me the other operator, given the knowledge that the Q table learned. The next, which means the action of this model will be one move. So with the time, we will be updating our Q table, and this is going to guarantee that in final stage, we are going to select more efficiently our operators instead of just performing a predetermined order, and that's all. This is the reward formula that we developed. It's an asymmetric formula, as you can see. This is because this Q-learn has a specific formula. I mean, there are different formulas, and we opt for the Belmont update rule. And as you can see, we have this OR component, which is the reward component. So this reward component is mainly calculated by the difference from the incumbent solution with the next solution. So if we have negative, so we are going to penalize our learning table. This is the idea. Well, right now, so yeah, I have just a visual example just to facilitate here the process of absorbing all the concepts. This is a tool that my construction algorithm provided to me. So as you can see, the current cost that we are seeing here is very close to the best node. This is a 29 instance. It's very small, but it's just to facilitate the visualization. And here, the idea is just executing the algorithm. As you can see, my shaping process at K1 level was the OR OPT, is a specific, like a shuffling, a block of cities. And this was chosen by the randomically algorithm. And we operated the shaping process. So now, as we perturbed the solution, now we are at the reinforcement learning stage, which is the intensification, which is the local search. So now our Q table is going to be updated with the time. Now I just executed the one move insertion. As you can see, it's all blank. It's all zero because it's the initialization of the table. It's all zero. But as we move along, we are going to see different values in our table. This is in green because we proved our solutions. Our previous solutions was 2567, now 2569. So we improved by using 3OPT, and then we one move, and then we move along with the 3OPT. This movement cause this type of rewarding, let's say. And then again, we are executing the 2OPT, and we improve it again. And finally, our table is populated with all the values during our executions till it reaches the best known solution, or until it reaches our criteria, termination criteria, that we define a bunch of criteria. The experimental setup, so we conducted different tests. Basically, our idea is to compare, the components that has adaptive variance with the non-adaptative ones. For example, the first one, it has a restrict candidate list as an initialization algorithm, and with the standard DNS. And then the fourth, as you can see, it's the fully adaptative test we executed. So here we have different type of parameters, different type of configurations. We executed for 10 instances. This is because our idea is to compare with the literature, and most of papers we studied use the same type of instance. That was the purpose in our work. Here is just to emphasize that the VND is being replaced by our reinforcement learning algorithm. So the VND is executed for these two experiments you are seeing over here, and the RL local search is being executed in these last two experiments. The results. So the results was quite good in terms of gaps. We are showing just 4 examples because for the other examples, we achieved 0 gap. For 30 executions, we execute for each type of instance, we reached the best known solution, different from papers on literature we found out. But in terms of time consumption, for certain types of instance, our fully adaptative component reached larger times than the other ones. So this is expected because this reinforcement learning, it aggregates overhead in terms of computational time, but it pays off sometimes because the gap is super small in terms in percent of speaking. Sometimes we need to let's say tune our parameters to achieve better results in terms of time as well. Our conclusions is that basically the reinforcement learning integration preserves this strong capability to achieve lower gaps for small and medium instances, and for larger ones it achieves gaps majority of the time, but increase time this overhead. And our future directions indicates hybrid learning situations where we can combine offline training with this online training. And we are aiming to extend this type of work to other type of problems different from TSP. And that's it. I think I'm on time. I don't know. So thank you very much.
Thank you for summarizing a lot of work. I only have one quick question. Are you going to the wine tasting?
Sorry?
Are you going to the wine tasting?
Yes.
Okay, so all of you can ask questions here because we are late in time. Thank you again.
Thank you.
Now we'll ask Anna to close this.
I'm sorry not being here during the workshop sessions. But
you are organizing the conference.
Yes, or organization workshop. So thank you all, and thank you, Humberto and Elisius, for sharing the sessions today. And I hope you are enjoying the conference and will enjoy the wine tasting and the other events and the other sessions, of course.
Yes.
Thank you very much.
Thank you. I will just add, submit next year.
Yes.
It's always good to have the same faces and new faces, and submit next year.
Yes.
Thank you. And I would like to thank our supporter here. It was very helpful. Thank you. Thanks.
So we have buses at 6.
And then 6:30 there, right?
6:15 here, that goes to the hotel.
Okay.
And this.
Very good.
Ok. Também vai ir a casa?
Nada, vou para Bolinhoso buscar a minha filha.
Mais vais a nada. Olha, e meter ali, tens a minha chavinha?
Aqui.
Olha, foi amanhã voltamos outra vez para o almoço.
Mas o Cássio não pode, eu não quero ir sozinho.
We need to move.
O Zé Manuel mudou.